Welcome back. Tonight, we settle in with the distant companions that drift in silence around worlds far larger than themselves, those patient, cratered spheres we call moons, each one tracing its own unhurried orbit through the dark, some wrapped in ice, others scarred by ancient collisions, a few hiding oceans beneath frozen shells. We will move slowly tonight, visiting these quiet attendants one by one, learning their names, their surfaces, the gentle pull that keeps them circling, forever bound to planets they will never touch. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the early weeks of the year 1610, in the northern Italian city of Padua, a professor of mathematics named Galileo Galilei turned a small telescope toward the night sky and, in doing so, began to unravel centuries of certainty about the heavens. The telescope itself was not his invention, having emerged from the workshops of Dutch spectacle makers only a year or two earlier, but Galileo had refined the instrument considerably, grinding his own lenses with careful attention until he had achieved a magnification of approximately 20 times, which was quite remarkable for its day. On the evening of January the 7th, he directed this improved device toward Jupiter, that bright wandering star known to astronomers since antiquity, and what he observed would prove to be among the most consequential sightings in the entire history of human understanding of the cosmos. What Galileo saw that cold January evening appeared, at first glance, to be rather unremarkable, merely 3 small points of light arranged in a neat line near the bright disk of Jupiter, 2 positioned to the east of the planet and 1 to the west. He noted these objects in his observational records with the calm precision of a man accustomed to documenting celestial phenomena, assuming initially that he had simply observed 3 fixed stars that happened to lie along Jupiter's path through the heavens. Fixed stars were understood to be permanent features of the celestial sphere, unchanging in their positions relative to one another, and so Galileo had no particular reason to suspect that these 3 faint points of light were anything other than distant suns, far too dim to be seen with the unaided eye but brought into visibility by his optical instrument. The following evening, however, Galileo returned to his telescope and directed it once again toward Jupiter, perhaps out of simple curiosity, perhaps with the intention of making additional measurements, and what he found must have given him pause. The 3 small stars were still present near Jupiter, but their arrangement had changed rather noticeably, with all 3 now positioned to the west of the planet rather than distributed on either side. This was peculiar, because Jupiter's motion through the sky should have carried it eastward relative to any fixed background stars, and yet these 3 points of light seemed to have shifted in the opposite direction from what one would expect. Galileo, being a careful observer, considered various explanations for this discrepancy, including the possibility that his earlier observations had contained some error, or that the astronomical tables he was using to predict Jupiter's motion were themselves inaccurate. On the nights that followed, Galileo continued his observations with growing fascination, watching as these mysterious points of light continued to change their positions relative to Jupiter in ways that could not be explained by the planet's own movement against the background stars. Sometimes only 2 of the objects were visible, sometimes 3, and on January the 13th, Galileo observed a 4th point of light that he had not noticed before, bringing the total number of these wandering stars to 4. By this time, the explanation had become clear to him, as clear as anything could be to a mind trained in mathematical reasoning and unafraid to follow evidence wherever it might lead. These were not fixed stars at all, but rather moons, small bodies that orbited around Jupiter just as our own moon orbits around the Earth, and their apparent changes in position from night to night were simply the result of their orbital motions carrying them sometimes to one side of Jupiter and sometimes to the other. This realization was profound in ways that extended far beyond the simple cataloguing of celestial objects, because for more than 1,000 years, European astronomy and natural philosophy had been built upon the assumption that the Earth occupied a unique and privileged position at the center of all creation, with everything in the heavens, the moon, the sun, the planets, and the stars, revolving around it in stately circular paths. This geocentric model, developed most fully by the ancient Greek astronomer Claudius Ptolemy and endorsed by the theological authorities of the Christian Church, held that the Earth was fundamentally different from all other celestial bodies, being the only object in the universe around which other things could orbit. And yet here, visible to anyone who cared to look through a modest telescope, was direct evidence that Jupiter possessed companions of its own, small worlds that circled around it just as the Moon circles around the Earth, proving beyond any reasonable dispute that our planet was not the only center of orbital motion in the cosmos. Galileo understood immediately the significance of what he had discovered, and he worked quickly to compile his observations into a small book that he titled Sidereus Nuncius, which translates from the Latin as something like starry messenger or perhaps message from the stars, and which he published in Venice in March of 1610, only 2 months after his initial sighting. The book was a slim volume, written in accessible Latin prose and illustrated with Galileo's own drawings of the Moon's cratered surface and the changing positions of Jupiter's 4 companions, and it caused an immediate sensation throughout learned Europe. Copies were eagerly sought by astronomers, philosophers, and curious laypeople alike, and within weeks the findings had been replicated by observers in other cities who possessed telescopes of their own, confirming that Galileo had indeed discovered something real and not merely an artifact of his optical instrument. In naming his discovery, Galileo chose to honor the powerful Medici family of Florence, rulers of the Grand Duchy of Tuscany, calling the 4 moons the Medicean stars in tribute to Cosimo II, the young Grand Duke who would become Galileo's patron and protector in the years ahead. This was a common practice in the astronomy of the period, as naming celestial objects after wealthy and influential patrons could secure financial support and political protection for scientific work that might otherwise be viewed with suspicion by religious or civil authorities. The name Medicean stars served Galileo well in this regard, helping to secure his appointment as court mathematician and philosopher to the Medici, but it did not endure as the standard designation for Jupiter's 4 large moons, being gradually replaced over the following centuries by a different set of names with a rather different origin. The German astronomer Simon Marius, who worked in the Margraviate of Ansbach, claimed to have observed Jupiter's moons independently and indeed slightly earlier than Galileo, a claim that led to bitter disputes between the 2 men and their respective supporters. Modern historians generally credit Galileo with priority in publication and systematic observation, though Marius may well have seen the moons around the same time through his own telescope. What is certain is that Marius proposed an alternative naming scheme in his 1614 book Mundus Ioviolus, or the World of Jupiter, drawing upon classical mythology to designate the 4 moons as Io, Europa, Ganymede, and Callisto, each name taken from the stories of lovers and companions of the god Jupiter in Greek and Roman legend. These mythological names did not immediately supplant the Medicean stars in common usage, but they gradually gained acceptance over the following 2 centuries, and by the mid-1800s they had become the standard designations that we still use today, honoring the mythical figures whose names now circle endlessly around the greatest of the planets. The theological implications of Galileo's discovery were deeply troubling to many scholars and churchmen of the early 17th century, not because the moons themselves posed any direct challenge to religious doctrine, but because they demonstrated so clearly that the Earth could not be the sole center around which all celestial motions occurred. If Jupiter could possess orbiting companions, then the Earth's moon was no longer unique, and the argument that our world must be the center of everything because it was the only body with a satellite became impossible to sustain. This lent powerful support to the heliocentric model of the solar system proposed by Nicolaus Copernicus in the previous century, which held that the Earth and other planets all orbited around the Sun, reducing our world from the center of creation to merely one planet among several. Galileo would later face severe consequences for his advocacy of Copernican ideas, being tried by the Roman Inquisition and forced to recant his views under threat of imprisonment, but the evidence he had gathered could not be unseen, and the slow acceptance of heliocentrism continued throughout the 17th century despite official opposition. One of the most remarkable aspects of Galileo's discovery was its accessibility, the fact that anyone with a decent telescope could replicate his observations and see for themselves the 4 small points of light dancing attendance upon Jupiter. Unlike many scientific discoveries, which require elaborate equipment or specialized training to verify, the Galilean moons can be observed with quite modest optical instruments, even a good pair of modern binoculars being sufficient to reveal them as tiny specks of light arranged near Jupiter's bright disk. This democratization of astronomical observation was something genuinely new in the history of science, because it meant that the evidence for heliocentrism was not hidden away in the calculations of learned mathematicians or the pronouncements of ancient authorities, but was available to anyone willing to look upward on a clear night and see with their own eyes that other worlds existed with companions of their own. Galileo's initial confusion about the number of moons he had discovered, thinking at first that there were 3 and only later recognizing the 4th, illustrates the care and patience required in astronomical observation, where objects may sometimes be too close to a bright planet to be distinguished, or may temporarily pass behind or in front of it and disappear from view entirely. Over the course of those January nights in 1610, as Galileo tracked the wandering positions of these tiny lights, he was developing observational techniques that would serve astronomers for centuries to come, learning to account for the limitations of his instrument, to distinguish real phenomena from optical artifacts, and to recognize patterns in motion that revealed the underlying orbital mechanics at work. His careful notes and drawings from those winter evenings in Padua remain valuable historical documents, showing us not just what he saw but how he thought about what he was seeing, how he moved from initial puzzlement through hypothesis and observation to confident understanding. The telescope that Galileo used for these observations would seem extremely crude by modern standards, producing images that were blurry around the edges and limited to a very small field of view, yet it was sufficient to reveal the fundamental truth that Jupiter possessed a miniature system of worlds orbiting around it, a truth that helped to reshape humanity's understanding of its place in the universe. In the 4 centuries since those January nights in Padua, we have sent spacecraft to orbit Jupiter and fly past these 4 moons, photographing their surfaces in extraordinary detail and discovering that they are not merely points of light but genuine worlds, each with its own character and history and mysteries waiting to be explored. But all of that began with a middle-aged professor peering through a tube of leather and glass on a cold Italian night, noting down the positions of a few faint stars, and wondering why they refused to stay in their proper places. In the year 1655, a Dutch astronomer named Christiaan Huygens turned a telescope of his own design toward the planet Saturn, and in doing so, he became the first person to observe a world that would, centuries later, prove to be one of the most remarkable places in our entire solar system. Huygens was working with a refracting telescope that offered a magnification of approximately 50 times, which was, for that era, a considerable achievement in optical craftsmanship, and through this instrument, he noticed a small point of light that moved in a regular pattern around the ring planet, completing one orbit roughly every 16 days. He announced his discovery in an anagram, as was the custom among natural philosophers of his time who wished to establish priority while continuing their observations, and when he decoded his message the following year, the world learned of a new moon, the largest and brightest satellite of Saturn, which would eventually bear the name Titan, after the ancient Greek deities who preceded the Olympian gods. For more than 300 years following that initial sighting, Titan remained a distant speck of light, a small golden point moving faithfully around its parent planet, and astronomers could do little more than refine their measurements of its orbit, estimate its size, and wonder what manner of world it might be. Some observations in the early 20th century hinted at the presence of an atmosphere, a suggestion that was confirmed in 1944 when Gerard Kuiper detected the spectral signature of methane gas, making Titan the only moon in our solar system known at that time to possess a substantial atmosphere. But the true nature of this distant world, its surface, its weather, its seas, all of these remained hidden beneath a thick and impenetrable haze that no Earth-based telescope could pierce, and so Titan kept its secrets for generation after generation, patient and unhurried in its orbit around Saturn, waiting for the day when humanity would send machines to look more closely. That day arrived on the 12th of November, 1980, when the Voyager 1 spacecraft swept past the Saturn system after a journey of more than 3 years from Earth. As the probe approached Titan, scientists hoped to glimpse the surface of this intriguing moon, but what they found instead was a world completely shrouded in orange haze, a thick atmosphere so opaque that not a single surface feature could be seen in visible light. However, this apparent disappointment was in fact a profound discovery, for Voyager's instruments revealed an atmosphere far denser and more complex than anyone had anticipated. The atmospheric pressure at Titan's surface, the spacecraft determined, is approximately 1.5 times that of Earth at sea level, meaning that if you were to stand on Titan, you would feel a slightly greater weight of air pressing down upon you than you do here on our own planet. even though Titan itself is a much smaller world with considerably weaker gravity. The composition of this thick atmosphere proved to be predominantly nitrogen, comprising roughly 95% of the total, with methane making up most of the remainder, along with traces of other hydrocarbons such as ethane, propane, and various more complex organic molecules. This was, and remains, the only other dense nitrogen atmosphere in our solar system besides Earth's, a curious kinship between our warm, watery world and this frigid moon orbiting so far from the Sun. The Voyager data also revealed that the orange color that gives Titan its distinctive appearance comes from a complex mixture of organic molecules suspended high in the atmosphere, compounds that scientists call tholins, a word derived from the Greek for muddy or turbid. These tholins form when ultraviolet light from the distant Sun and energetic particles from Saturn's magnetosphere break apart the methane and nitrogen molecules in Titan's upper atmosphere, and the resulting fragments recombine into larger and more complex organic compounds that slowly drift downward through the atmosphere like an endless, gentle snow of primordial chemistry. The temperature at Titan's surface, measurements have shown, hovers around -179 degrees Celsius, which is approximately 94 Kelvin, far colder than any natural environment on Earth and cold enough that water ice is as hard as rock and remains permanently frozen. At these temperatures, methane and ethane, which are gases on Earth, can exist as liquids, and this realization led scientists to wonder whether Titan might possess not only an atmosphere with weather, but also bodies of liquid on its surface, seas, and lakes and rivers composed not of water but of hydrocarbons, flowing and pooling and perhaps even raining down from the orange skies. To answer these questions and to finally see what lay beneath that impenetrable haze, the space agencies of the United States and Europe collaborated on one of the most ambitious planetary missions ever conceived. The Cassini-Huygens mission, named in honor of the 17th century astronomer Giovanni Cassini as well as Christian Huygens himself, launched from Earth in October of 1997 and arrived at Saturn nearly 7 years later in July of 2004. The mission consisted of two components, an orbiter called Cassini that would spend years exploring the Saturn system, and a landing probe called Huygens that would descend through Titan's atmosphere and, for the first time in history, touch down upon the surface of a moon in the outer solar system. On the 25th of December, 2004, the Huygens probe separated from its parent spacecraft and began a 3-week coast toward Titan, falling silently through the vacuum of space toward its appointment with that cloud-wrapped world. Then, on the 14th of January, 2005, the probe entered Titan's atmosphere at a speed of roughly 6 kilometers per second, protected by a heat shield that absorbed the fierce energies of deceleration, and as it slowed, a sequence of parachutes deployed to further gentle its descent. For approximately 2 hours and 27 minutes, the Huygens probe drifted downward through the orange haze, its instruments measuring the temperature, pressure, and composition of the atmosphere at every altitude, while its cameras captured images of the landscape slowly emerging from the mist below. What those cameras revealed was a world both alien and strangely familiar. The images showed a surface carved by flowing liquids, with drainage channels and river networks etched into the terrain, branching and merging in patterns immediately recognizable to anyone who has seen aerial photographs of river deltas on Earth. The liquid that carved these channels was not water, of course, but rather liquid methane, and the dark material that collected in the lowlands was composed of hydrocarbon sediments washed down from the higher ground. As the probe descended below the main haze layer at an altitude of roughly 30 kilometers, visibility improved dramatically, and the cameras captured increasingly detailed views of the landscape, including what appeared to be a shoreline separating brighter highland terrain from darker lowland areas. The Huygens probe touched down on Titan's surface at a speed of approximately 5 meters per second, a gentle landing that the probe survived without difficulty, and for another 72 minutes it continued to transmit data from the surface before its batteries were finally exhausted and it fell silent forever. The landing site proved to be a relatively flat plain scattered with rounded pebbles and cobbles of water ice, smoothed by some unknown process, perhaps tumbling in ancient floods of liquid methane or worn by the slow abrasion of wind-blown particles. The surface had a thin crust that gave way slightly under the probe's impact, suggesting a consistency somewhat like damp sand or wet clay, and beneath this crust was a layer of material with a different composition, possibly ice mixed with hydrocarbon compounds. The Huygens landing was, and remains, the most distant landing ever achieved by any spacecraft from Earth, a gentle arrival on a world nearly 1.5 billion kilometers from home, and the data it returned has shaped our understanding of Titan for the 2 decades since. Meanwhile, the Cassini orbiter continued its exploration of the Saturn system, making repeated close approaches to Titan over the course of 13 years and using radar instruments to peer through the thick atmosphere and map the surface below. These radar observations revealed a world of astonishing variety, with vast plains of organic sediment, mountain ranges of water ice, and, most remarkably, hundreds of lakes and seas filled with liquid hydrocarbons. The largest of these seas, located near Titan's North Pole, bears the name Kraken Mare, after the legendary sea monster of Norse mythology, and it covers an area of roughly 400,000 square kilometers, making it larger than the Caspian Sea on Earth and containing enough liquid methane and ethane to constitute the largest known body of liquid on any world other than our own. Nearby lies Ligeia Mare, the second largest of Titan's seas, with depths measured by Cassini's radar that reach at least 160 meters, though the true maximum depth may be greater still, and the liquid that fills the sea is remarkably pure, composed almost entirely of methane with very little ethane mixed in, as clear and transparent as any earthly lake. In the southern hemisphere, the smaller Ontario Lacus, named for its similarity in size and shape to Lake Ontario on the border of Canada and the United States, provided early evidence that liquids exist on both poles of Titan, though the north appears to be far wetter than the south, possibly due to long-term cycles in Titan's climate driven by variations in its orbit around Saturn. During its years of observation, the Cassini spacecraft detected something peculiar in Ligeia Mare, a feature that appeared and disappeared and changed its shape over the course of several radar passes between 2013 and 2014. Scientists informally called this phenomenon a magic island, though it is almost certainly not an island at all, and various explanations have been proposed to account for the transient brightenings observed in the radar data. Some researchers suggest that waves on the surface of the sea, stirred by winds that strengthen during Titan's long summer, could create roughness sufficient to scatter the radar signal differently than a calm surface would. Others have proposed that streams of bubbles, perhaps nitrogen coming out of solution as the sea warms during the changing seasons, might rise to the surface and create temporary patches of radar-bright froth. Still others suggest that suspended solids, organic particles drifting through the liquid, might account for the phenomenon. The true explanation remains uncertain, but the very existence of such transient features speaks to the dynamic nature of Titan's hydrocarbon seas, bodies of liquid that are not static and unchanging but rather respond to winds, temperatures, and seasonal cycles, much as the oceans and lakes of Earth respond to the rhythms of our own world. Beyond the lakes and seas, Titan may also possess another form of liquid activity, a phenomenon that scientists call cryovolcanism, or cold volcanism, in which the molten rock of earthly volcanoes is replaced by mixtures of water and ammonia that erupt from the interior onto the frozen surface. Several features observed by Cassini, including elevated structures with flow-like morphologies and unusual spectral signatures, have been proposed as possible cryovolcanic constructs, though the evidence remains somewhat ambiguous and the scientific community has not yet reached consensus on whether cryovolcanism is truly active on Titan today or whether it occurred only in the distant past. If such activity does occur, it would represent a means by which materials from Titan's interior, including water and ammonia and perhaps more complex compounds, could be delivered to the surface and mixed with the organic molecules raining down from the atmosphere, creating environments where chemistry of considerable complexity might take place. This brings us to one of the most intriguing aspects of Titan as a world, namely its potential relevance to the question of how life begins. The conditions on Titan's surface today are far too cold for the water-based biochemistry that we know from Earth, as liquid water cannot exist there except perhaps briefly in the aftermath of an impact or a cryovolcanic eruption. However, the organic chemistry occurring in Titan's atmosphere and on its surface is extraordinarily rich, producing a vast array of complex molecules that are, in a sense, precursors to the molecules of life. Some scientists have speculated that Titan's environment today might resemble, in certain ways, the environment of the early Earth before life arose, when our own atmosphere was rich in reducing compounds and organic chemistry was widespread. Studying Titan, these researchers suggest, might offer insights into the processes that set the stage for life on our own world billions of years ago. Others have raised the more speculative possibility that some form of exotic chemistry, quite different from the water-based biochemistry we know, might be capable of producing something we would recognize as life even in Titan's frigid hydrocarbon seas, though this remains firmly in the realm of hypothesis rather than observation. For now, Titan continues its slow orbit around Saturn, turning once every 16 days just as Huygens observed nearly 4 centuries ago, its thick orange atmosphere catching the faint light of the distant sun, its methane rains falling softly onto landscapes of ice and organic sediment, its dark seas rippling perhaps with waves we cannot see. The Huygens probe rests silently on its plain of rounded pebbles, its mission long since complete, while high above, the seasons turn over decades, and the North Polar seas slowly warm as summer arrives. Future missions are being planned to return to this extraordinary world, to sail its seas with floating probes, to fly through its thick atmosphere with drone-like rotorcraft, to sample its complex chemistry and search for answers to questions we are only beginning to ask. But for tonight, it is enough to know that Titan is there, a moon with weather and seas, a world wrapped in orange haze, a place both utterly alien and strangely, comfortingly familiar, waiting patiently for whatever may come next. Europa is one of the 4 large moons of Jupiter, discovered by Galileo Galilei in the year 1610, and it has become, in the century since, one of the most quietly compelling objects in our solar system, not because it is the largest or the most visually dramatic, but because of what may lie beneath its pale and fractured surface. This moon is only slightly smaller than our own moon, measuring approximately 3,100 kilometers across, and yet it holds within it the possibility of an ocean, a vast body of liquid water hidden beneath a shell of ice, and this possibility has transformed the way we think about where life might exist beyond our own small world. As you settle in and let your thoughts drift gently, we will explore what we have learned about Europa, how scientists first came to suspect the presence of this hidden sea, and what missions past and future have revealed and may yet reveal about this distant icy moon. The story of Europa's ocean begins, in a sense, with the Voyager spacecraft, those twin explorers that departed Earth in 1977 and journeyed outward through the solar system, returning images and data that reshaped our understanding of the outer planets and their many moons. When Voyager 1 and Voyager 2 flew past the Jupiter system in 1979, they captured the first detailed images of Europa's surface, and what they showed was unexpected and quietly remarkable. Unlike many moons in the outer solar system, which are heavily scarred by impact craters accumulated over billions of years, Europa's surface appeared relatively smooth and young, marked not by countless craters but by an intricate network of long, curving lines and cracks, a pattern that resembled nothing so much as a cracked eggshell or the fractured surface of sea ice here on Earth. The relative absence of craters suggested that the surface was being renewed in some way, that geological processes were erasing the ancient scars and replacing them with fresh terrain, and this observation led scientists to begin considering what might be happening beneath that icy exterior. It was after the Voyager encounters that the hypothesis of a subsurface ocean on Europa began to be taken seriously within the scientific community. The fractured appearance of the ice, the patterns of ridges and grooves crisscrossing the surface, and the apparent youth of the terrain all pointed toward a dynamic world, one where the ice shell might be floating upon or interacting with a layer of liquid water below. This idea, which might once have seemed fanciful, gradually gained support as researchers developed models of Europa's interior and began to understand the forces that could keep water liquid so far from the warmth of the sun. The notion of an ocean hidden beneath kilometers of ice is now considered not merely plausible but likely, and it is this possibility that has made Europa a place of such quiet fascination. The thickness of Europa's ice shell has been the subject of considerable study and some debate, as different lines of evidence have pointed to different estimates. Based on analyses of surface features, theoretical models of heat transfer, and interpretations of various spacecraft data, scientists generally believe that the ice shell is somewhere between 10 and 30 kilometers thick, though some models have suggested it could be thinner in places or somewhat thicker in others. Beneath this shell, The ocean itself is thought to be remarkably deep, with estimates suggesting it could extend downward for 60 to 150 kilometers before reaching the Moon's rocky interior. If these estimates are correct, then Europa's ocean, despite being hidden from view, could contain more than twice the volume of all of Earth's oceans combined, a staggering quantity of liquid water held in the darkness beneath the ice. The depth and extent of this ocean, inferred rather than directly observed, remind us how much of the universe remains unseen and yet within the reach of careful scientific inquiry. Among the most intriguing features on Europa's surface are the regions known as chaos terrain, areas where the ice appears to have been disrupted, broken into blocks, and refrozen in new configurations. One of the best-studied examples of chaos terrain is a region called Connemara Chaos, named after a place in Ireland, which was imaged in detail by the Galileo spacecraft in the 1990s. In Connemara Chaos, the surface is composed of irregularly shaped ice blocks, some of them several kilometers across, that seem to have shifted and rotated from their original positions before becoming locked again into the surrounding ice. The appearance of this terrain is strikingly similar to what one might see in images of pack ice on Earth's polar seas, where floating ice rafts jostle against one another and refreeze into new arrangements. The presence of such features on Europa has been interpreted as evidence that the ice shell has, at least at times and in certain places, been thin enough or warm enough to allow blocks of ice to float and move upon an underlying liquid layer. This process, sometimes called ice rafting, suggests a dynamic relationship between the surface ice and the ocean below, a relationship that may have allowed material to be exchanged between the two over geological time. The question of how Europa's ocean remains liquid is answered, at least in part, by a process called tidal heating. Europa orbits Jupiter at a distance of approximately 670,000 kilometers, completing one orbit every 3.5 Earth days, and as it travels along this path, it is subject to the immense gravitational pull of its parent planet. Jupiter's gravity exerts tidal forces on Europa, stretching and compressing the Moon's interior as it moves closer to and farther from Jupiter during each orbit. This repeated flexing generates heat within Europa's interior, much as bending a piece of metal back and forth will cause it to warm, and this tidal heating is thought to be sufficient to keep the ocean liquid despite the extreme cold of the outer solar system, where surface temperatures on Europa hover around -160 degrees Celsius. The ice shell acts as an insulating blanket, trapping the heat produced in the interior and allowing liquid water to persist beneath the frozen surface. It is a gentle and continuous process, one that has likely been operating for billions of years, maintaining the ocean in a state of quiet stability far from the light of the sun. Further evidence for the existence of Europa's ocean came from the Galileo spacecraft, which orbited Jupiter from 1995 to 2003 and made numerous close passes by the Galilean moons. In 1997, during one of its flybys of Europa, the spacecraft's magnetometer instrument detected something unusual and significant. The data showed that Europa was generating an induced magnetic field, a secondary field created in response to Jupiter's powerful rotating magnetic field, and this induced field had characteristics that were best explained by the presence of a global layer of electrically conducting material beneath the ice. Ordinary ice is a poor conductor of electricity, but salty water, like the seawater found in Earth's oceans, is an excellent conductor, and the magnetometer data thus provided strong indirect evidence that Europa's ocean is not only present but is salty, containing dissolved minerals that allow it to conduct electrical currents. This finding, announced by the Galileo science team, was a quiet but profound moment in planetary exploration, as it transformed the subsurface ocean from a hypothesis into something approaching a well-supported conclusion. Observations from Earth-based and orbital telescopes have added further layers to our understanding of Europa and its hidden ocean. In 2012, astronomers using the Hubble Space Telescope reported the detection of possible plumes of water vapor erupting from Europa's surface, rising to heights of approximately 200 kilometers above the Moon's south polar region before falling back. These plumes, if confirmed, would indicate that water from the subsurface ocean or from pockets of liquid within the ice shell is occasionally venting into space, creating transient features that disperse and disappear over time. The initial detection was tentative, as the plumes were faint and difficult to observe, but subsequent Hubble observations in 2016 provided additional supporting evidence, capturing what appeared to be similar plume activity in the same general region. The existence of such plumes is significant not only as further evidence of liquid water, but also because they might offer a way to sample the ocean's contents without drilling through kilometers of ice, by flying a spacecraft through the plume and analyzing the particles and gases it contains. The scientific community has recognized the importance of Europa for many years, and this recognition has led to the development of a dedicated mission to study the Moon in unprecedented detail. The Europa Clipper spacecraft, developed by NASA, was launched in October of 2024 and is now making its way toward the Jupiter system, where it will arrive after a journey of several years. Unlike an orbiter that would circle Europa continuously, the Europa Clipper is designed to remain in orbit around Jupiter and to make repeated close flybys of Europa, 49 of them planned in total, each pass gathering data with a suite of scientific instruments before the spacecraft retreats to a safer distance from Jupiter's intense radiation belts. This approach allows the mission to study nearly the entire surface of Europa over time, building up a comprehensive picture of the Moon's ice shell, its surface geology, and any plume activity that may be occurring. The instruments aboard Europa Clipper include cameras, spectrometers, a magnetometer, an ice-penetrating radar, and other tools designed to probe the nature of the ice shell, the depth and salinity of the ocean, and the composition of any material that may be escaping into space. It is a mission shaped by decades of accumulated knowledge and by the questions that remain unanswered, a patient endeavor befitting a world that has kept its secrets hidden beneath the ice. Among the scientists who have contributed to our understanding of Europa's potential as a habitable world, the work of Richard Greenberg deserves particular mention. Greenberg, an American planetary scientist, devoted considerable effort to studying the interaction between Europa's surface and its subsurface ocean, exploring the ways in which material might be exchanged between the two environments. His research addressed questions such as how quickly the ice shell might overturn or recycle, whether cracks in the ice could provide pathways for water or nutrients to reach the surface or for surface material to reach the ocean below, and what these processes might mean for the possibility of life. Greenberg argued that the tidal forces acting on Europa could create a dynamic ice shell, one that is not merely a static barrier but an active participant in the Moon's geology, opening and closing cracks, circulating material, and potentially delivering the chemical ingredients necessary for life from the surface, where they are produced by radiation, down into the dark ocean. His work emphasized that habitability is not simply a matter of having liquid water, though that is essential, but also of having the energy sources and chemical building blocks that life requires, and he suggested that Europa's tidal activity might provide all of these in sufficient measure. Though the question of whether life exists on Europa remains unanswered, the framework that Greenberg and others have developed has helped to clarify what conditions might be present and what future missions should look for. As you allow your breathing to slow and your thoughts to settle, you might imagine Europa as it is now, a small pale moon circling endlessly around the great banded sphere of Jupiter, its surface bright with reflected sunlight, its interior dark and hidden. Beneath the cracked and refrozen ice, an ocean waits, cold and salty and utterly unknown, stirred perhaps by currents we cannot see, warmed by the gentle but persistent flexing of tidal forces. Whether that ocean is lifeless or whether it harbors some form of life, simple or strange, is a question that may not be answered for many years, but the search itself is a kind of gift, a reminder that the universe is vast and that even within our own solar system there are worlds we have only begun to understand. The Europa Clipper, now journeying outward through the darkness, carries with it the instruments and the intentions of countless researchers, the accumulated curiosity of generations, and it will, in time, send back new data, new images, and perhaps new surprises from that distant frozen moon. For now, Europa remains quiet, patient, and unknowably deep, and you may rest with the thought of it, a world of ice and hidden water, waiting beneath the light of a distant sun. In the cold outer reaches of our solar system, far beyond the familiar orbits of Jupiter and Saturn, there exists a world of profound stillness and ancient mystery. Triton, the largest moon of Neptune, drifts through the darkness at a distance so vast that sunlight takes more than 4 hours to reach it, and when that light finally arrives, it carries only a fraction of the warmth we feel here on Earth. This is a place of extreme cold, of frozen nitrogen plains, and of geological processes that operate on timescales almost impossible to comprehend. And yet, for all its remoteness, Triton has revealed itself to be one of the most fascinating objects in our solar system, a world with a violent past and an inevitable, patient future. The story of Triton's discovery begins with the discovery of Neptune itself, and it is a story that moves with remarkable speed by the standards of astronomical history. On the 23rd of September in 1846, the German astronomer Johann Galle peered through the telescope at the Berlin Observatory and found Neptune precisely where mathematical calculations had predicted it would be, a triumph of celestial mechanics and the power of mathematics to reveal unseen worlds. Just 17 days later, on the 10th of October of that same year, the English astronomer William Lassell turned his own telescope toward the newly discovered planet and noticed something else, a faint point of light moving in concert with Neptune, clearly in orbit around it. This was Triton, named after the son of Poseidon in Greek mythology, a sea god who served as herald to his father, and the name seemed fitting for a moon attending the planet named for the Roman god of the sea. William Lassell was a brewer by trade, having made his fortune in the ale business in Liverpool, but his true passion lay in the construction of telescopes and the observation of the heavens. He had built his own reflecting telescope, a magnificent instrument with a mirror 2 feet in diameter, and he had developed innovative techniques for polishing and mounting these mirrors that allowed him to observe fainter and more distant objects than many of his contemporaries. When news of Neptune's discovery reached him, Lassell wasted no time in directing his telescope toward this new world, and his diligence was rewarded almost immediately with the detection of Triton. It was a discovery that came with remarkable ease, in a sense, because Triton is by far the largest of Neptune's moons, containing more than 99% of all the mass orbiting the planet, and its brightness, though faint, was within reach of a skilled observer with good equipment. From the very beginning, there was something unusual about Triton's orbit. As astronomers tracked its motion over the following years and decades, they came to realize that this moon travels around Neptune in the wrong direction. Nearly all the large moons in our solar system orbit their planets in the same direction that those planets rotate, a consequence of the way moons typically form from the same spinning disk of material that created their parent planets. But Triton moves in retrograde, circling Neptune in the opposite direction to the planet's spin, and this peculiarity demands an explanation. A moon cannot simply form in a retrograde orbit through the normal processes of planetary formation, and so Triton must have come from somewhere else, arriving at Neptune through a process of gravitational capture that fundamentally altered the history of the Neptunian system. The most widely accepted explanation is that Triton originated in the Kuiper Belt, that vast reservoir of icy bodies that extends beyond the orbit of Neptune and stretches outward toward the even more distant reaches of the solar system. The Kuiper Belt is home to countless objects left over from the formation of the planets, frozen remnants of the primordial solar nebula that never coalesced into larger worlds, and Triton, with its composition of rock and ice and its size comparable to Pluto, fits the profile of a Kuiper Belt object rather well. At some point in the distant past, perhaps during the tumultuous period of planetary migration that reshaped the early solar system, Triton passed close enough to Neptune to be captured by the giant planet's gravity, and it has remained there ever since, a visitor from the outer darkness that became a permanent resident. The capture of Triton was almost certainly a catastrophic event for any moons that Neptune may have possessed before that time. When a large body like Triton enters a planetary system on a capture trajectory, its gravitational influence can destabilize the orbits of existing satellites, sending some crashing into the planet, flinging others out into interplanetary space, and generally wreaking havoc on any orderly arrangement that existed previously. Neptune does possess a number of smaller moons today, but they are tiny compared to Triton, and many of them may be fragments of larger bodies that were destroyed during Triton's arrival, or perhaps they formed afterward from debris left in orbit around the planet. The hypothesis that Triton destroyed Neptune's original moon system remains a subject of ongoing research and scientific discussion, but the circumstantial evidence is compelling, and it adds a note of ancient violence to the otherwise serene appearance of this distant world. For more than a century after its discovery, Triton remained little more than a point of light in even the most powerful telescopes, its surface features completely unknown, its composition a matter of speculation. Then, in the summer of 1989, everything changed. On the 25th of August of that year, the Voyager 2 spacecraft, which had already visited Jupiter, Saturn, and Uranus on its grand tour of the outer planets, made its closest approach to Neptune and flew past Triton at a distance of about 40,000 kilometers. This was the first and, to this day, the only spacecraft visit to the Neptunian system, and the images and data returned by Voyager 2 transformed our understanding of this frozen moon. What Voyager 2 revealed was a world of unexpected complexity and beauty. The surface of Triton proved to be among the youngest in the solar system, relatively speaking, with few impact craters marring its frozen plains. This youthful appearance indicated that geological processes must be at work, resurfacing the moon and erasing the record of ancient impacts, and the evidence for such activity was not difficult to find. Voyager 2 observed dark streaks on the surface, elongated markings that appeared to be deposits of material laid down by some kind of eruptive process, and further analysis confirmed that these were indeed the signatures of active geysers, columns of nitrogen gas and dark particles shooting upward from beneath the surface to heights of approximately 8 kilometers before being carried downwind by the thin atmosphere. These nitrogen geysers, or cryovolcanoes as they are sometimes called, operate through a mechanism that is both simple and elegant. Beneath the surface of Triton, solid nitrogen ice is slowly warmed by the faint sunlight that penetrates through translucent surface layers, much as sunlight can warm the interior of a greenhouse here on Earth. When this subsurface nitrogen reaches a critical temperature, it transforms from solid to gas, building up pressure beneath the frozen surface until it finally erupts through weak points in the overlying material, carrying dark particles of dust and organic compounds upward in towering plumes. The material falls back to the surface downwind of the eruption site, creating the distinctive dark streaks that Voyager 2 photographed, streaks that may persist for years or decades before being covered by fresh deposits of nitrogen frost. Among the most distinctive features observed on Triton is a type of terrain that exists nowhere else in the solar system, at least as far as we currently know. Scientists have given it the informal name of cantaloupe terrain, because its appearance bears a striking resemblance to the skin of that particular melon, with its network of crisscrossing grooves and rounded, dimpled cells. This terrain covers much of Triton's western hemisphere, and its origin has been the subject of considerable scientific investigation. The leading hypothesis is that it formed through a process called diapyrism, in which less dense material rises through denser overlying layers, creating dome-like structures that produce the characteristic dimpled appearance. On Earth, diapyrism is responsible for the formation of salt domes and some types of volcanic features, but on Triton, the rising material is likely to be ice of various compositions, and the process operates at temperatures and pressures vastly different from anything we experience here. The surface temperature of Triton is extraordinarily low, among the coldest measured anywhere in the solar system. During the Voyager 2 flyby, instruments recorded temperatures of approximately minus 235 degrees Celsius, which is just 38 Kelvin, or 38 degrees above absolute zero. At these temperatures, many substances that we think of as gases exist in solid form on Triton's surface. Nitrogen, which makes up the bulk of Earth's atmosphere, lies frozen on the ground as transparent or pinkish ice. Methane and carbon monoxide are also present as surface frosts, and these ices interact with the faint sunlight to produce subtle color variations that give Triton's surface its distinctive appearance, with regions of pink and white and pale blue spread across its frozen plains. Despite the extreme cold, Triton does possess an atmosphere, though it is so tenuous that calling it an atmosphere at all requires some generosity of definition. The surface pressure is approximately 14 microbars, which is about 70,000 times less than the atmospheric pressure at sea level on Earth, and yet this thin envelope of gas, composed primarily of nitrogen with traces of methane and carbon monoxide, is sufficient to produce observable effects. There is weather on Triton, in a sense, with clouds and hazes observed in the atmosphere, and the geysers that erupt from the surface interact with this thin air, their plumes being bent and dispersed by the weak but measurable winds that blow across the frozen landscape. The atmosphere of Triton also exhibits seasonal changes, though these seasons proceed at a pace that would try the patience of any earthly observer. Neptune takes approximately 165 Earth years to complete a single orbit around the Sun, and Triton seasons are tied to this orbital period, with polar caps of nitrogen ice growing and shrinking as different regions of the Moon are exposed to slightly more or slightly less sunlight over the course of decades. There is evidence that Triton's atmosphere thickens slightly during warmer periods, as more nitrogen ice sublimates from the surface into gas, and thins again during colder times, as the gas freezes back onto the ground. These changes are subtle and slow, operating on timescales far longer than a human lifetime, but they remind us that even in the coldest regions of our solar system, change is constant, and no world is truly static. As we contemplate Triton's present, it is worth also considering its future, for this moon's fate is sealed by the very orbital mechanics that make it so unusual. Because Triton orbits in a retrograde direction, tidal forces between it and Neptune act to gradually slow its orbital velocity and cause it to spiral slowly inward toward the planet. This process is inexorable but extraordinarily slow, and billions of years will pass before its consequences become apparent. Current calculations suggest that in approximately 3.6 billion years, give or take a few hundred million years, Triton will approach Neptune so closely that it will cross the Rush limit, the distance within which tidal forces exceed the Moon's own gravitational cohesion, and when that happens, Triton will be torn apart, its material spreading out to form a ring system around Neptune that would rival or perhaps even exceed the magnificent rings of Saturn. This eventual fate, though impossibly distant from our perspective, connects Triton to the broader cycles of creation and destruction that govern the evolution of planetary systems. Moons are captured, moons are destroyed, rings form and dissipate, and the arrangement of bodies around a planet is never permanent, only a snapshot of one moment in an endless process of change. Triton, which may have destroyed Neptune's original moons when it arrived, will itself be destroyed in the fullness of time, contributing its substance to a new phase of Neptunian evolution that no human eye will ever witness. For now, Triton continues its slow, backward orbit around Neptune, its geysers erupting silently into the thin air, its cantaloupe terrain preserving the record of geological processes we do not yet fully understand, its frozen surface glittering faintly in the distant sunlight. It remains one of the most intriguing worlds in our solar system, a captured wanderer from the outer darkness that has made its home around the farthest of the giant planets, and though only one spacecraft has ever visited it, the data returned by Voyager 2 continues to fuel scientific investigation and wonder more than 3 decades later. Perhaps one day another mission will make the long journey to Neptune and Triton, and perhaps new discoveries await that will deepen our understanding of this remarkable moon. But for tonight, it is enough to know that Triton is there, circling endlessly through the cold and the dark, a world of nitrogen ice and ancient mystery, waiting patiently at the edge of the solar system. In the year 1789, while much of the world concerned itself with revolutions and the upheavals of nations, a quiet observer in the English town of Slough turned his newly constructed telescope toward the pale golden disk of Saturn. William Herschel, the German-born musician who had transformed himself into one of the most accomplished astronomers of his age, was engaged in a systematic survey of the Saturnian system, and on the night of the 28th of August, he noticed a tiny point of light moving in concert with the ringed planet. This was not a fixed star drifting through the field of view, but something bound to Saturn itself, a small companion following its own orbital path. Herschel had discovered what would eventually be named Enceladus, after one of the giants of Greek mythology, a figure said to lie buried beneath Mount Etna, his restless stirrings blamed for volcanic tremors. The name would prove remarkably fitting, though Herschel could not have known this, for he saw only a faint speck of light, a moon so small and distant that almost nothing about its true nature could be discerned through the instruments of his era. For nearly 2 centuries, Enceladus remained little more than an astronomical footnote, a modest member of Saturn's extensive family of moons, notable primarily for its high reflectivity and its modest dimensions. The moon spans approximately 500 kilometers in diameter, which is to say it could fit comfortably within the borders of a medium-sized country or across a single large metropolitan region. When the Voyager spacecraft swept through the Saturnian system in the early 1980s, they returned images showing a surface that was puzzling in its smoothness, with vast plains that seemed remarkably free of the heavy cratering one might expect on such an ancient body. Scientists noted these features with interest but moved on to other mysteries, for the outer solar system was revealing itself to be far more complex than anyone had anticipated, and there were many worlds demanding attention. Everything changed in the year 2005, when the Cassini spacecraft, having arrived at Saturn the previous year, turned its instruments toward this small icy moon and observed something extraordinary. Erupting from the southern polar region of Enceladus were enormous plumes of material, great fountains of ice crystals and water vapor shooting hundreds of kilometers into space. This was not the gradual sublimation of surface ice that might occur on a frigid world, nor was it evidence of some ancient geological process frozen in time. These were active eruptions, happening in the present moment, cryovolcanism on a scale that demanded explanation. The discovery transformed Enceladus from a minor curiosity into one of the most compelling objects in the entire solar system, a tiny world that was geologically alive in ways that seemed almost impossible given its diminutive size. The source of these remarkable plumes was traced to a series of parallel fractures near the South Pole, for prominent rifts in the icy crust that came to be known informally as the tiger stripes due to their distinctive appearance in enhanced color images. These fractures were given formal names drawn from cities famous in the ancient world, places associated with learning and civilization, and so they became Baghdad Sulcus, Cairo Sulcus, Alexandria Sulcus, and Damascus Sulcus. Each of these features stretches approximately 130 kilometers in length and measures roughly 2 kilometers in width, and along their lengths, the ice has been fractured and deformed by forces welling up from below. The temperature along these stripes is notably warmer than the surrounding terrain, reaching perhaps -80 degrees Celsius in some locations, which is remarkably warm by the standards of a world where ambient surface temperatures hover around -200 degrees Celsius. Heat is escaping from the interior of this small moon, and with that heat comes the material that feeds the towering plumes. Over the following years, Cassini made numerous close passes by Enceladus, each flyby revealing new details about the nature of these eruptions and the world that produced them. But perhaps the most daring encounter came in October of 2015, when mission controllers sent the spacecraft on a trajectory that would carry it directly through the plumes themselves at an altitude of just 49 kilometers above the moon's surface. This was an act of calculated audacity, threading a spacecraft traveling at tremendous speed through a column of icy particles being ejected from an alien world, all in the hope of sampling the material directly. The instruments aboard Cassini opened their metaphorical mouths and tasted what Enceladus was offering, analyzing the composition of the plume material with a precision that no remote observation could match. What they found was water, predominantly, but also an array of other compounds that told a story of complex chemistry occurring somewhere beneath the frozen shell of this distant moon. In 2017, the analysis of data from these plume passages yielded a particularly significant finding: the detection of molecular hydrogen in the erupted material. Hydrogen in this context is not simply an interesting chemical curiosity, but rather a potential signature of specific processes occurring deep within Enceladus. On Earth, molecular hydrogen is produced when hot water interacts with certain types of rock in a process called serpentinization, which occurs at hydrothermal vents on the ocean floor, those strange oases of life that cluster around volcanic fissures in the deep sea. The presence of hydrogen streaming out of Enceladus suggests that similar processes may be occurring beneath its ice, that somewhere in the darkness of this moon's interior, hot water is reacting with rocky material, producing the chemical conditions that, on our own world, support thriving ecosystems entirely independent of sunlight. The picture that has emerged from decades of study is one of unexpected complexity. Beneath the frozen surface of Enceladus, beneath a shell of ice estimated to be roughly 30 to 40 kilometers thick, there appears to exist a global ocean of liquid water. This subsurface sea is perhaps 10 kilometers deep in places, though its exact dimensions remain the subject of ongoing refinement. The existence of this ocean was inferred initially from the way Enceladus wobbles slightly in its orbit, a libration that would be impossible if the Moon were frozen solid throughout, but which makes perfect sense if a liquid layer decouples the icy shell from the rocky core beneath. Subsequent analysis of the plume chemistry and the gravitational field of the Moon has only strengthened this conclusion. Enceladus possesses a hidden ocean, dark and pressurized, sandwiched between ice above and rock below, and in this ocean, water is apparently warm enough in places to remain liquid and to drive the cryovolcanic activity that feeds the southern plumes. Further evidence of what occurs at the boundary between this ocean and the rocky core came from the detection of silica nanoparticles in the plume material. These tiny grains, measuring only a few nanometers in size, form under very specific conditions, when silica-rich water rapidly cools after having been heated to temperatures of 90 degrees Celsius or higher. On Earth, such particles are found in association with hydrothermal systems, where superheated water percolates through rock and emerges bearing a chemical memory of its subterranean journey. The presence of these nanoparticles in the Enceladus plumes suggests that the Moon's ocean floor hosts active hydrothermal vents, places where hot fluids rise from the rocky interior, carrying minerals and heat into the overlying water. This is precisely the sort of environment that, on Earth, supports chemosynthetic life, organisms that derive their energy not from sunlight but from the chemical disequilibrium created when hot, mineral-laden water meets cold seawater. The plumes of Enceladus do not simply dissipate into the void once they leave the Moon's surface. Much of the material falls back to the surface, coating the terrain near the tiger stripes with fresh deposits of fine ice crystals, but a significant fraction escapes the weak gravitational grasp of this small world and enters orbit around Saturn itself. This escaped material forms a diffuse ring of ice particles encircling the planet, known to astronomers as the E-ring. Unlike Saturn's more famous rings, which are relatively compact and sharply defined, the E-ring is a broad, tenuous structure extending far from the planet's main ring system. It is the E-ring that gives Enceladus its brilliant reflectivity, for the Moon orbits within this ring and is constantly coated by the very material it ejects. The process is remarkably prolific, with estimates suggesting that Enceladus contributes approximately 600 kilograms of material per second to the E-ring, a continuous fountain feeding a structure that spans hundreds of thousands of kilometers. Without this ongoing contribution from the small Moon's cryovolcanic activity, the E-ring would disperse and fade over astronomical timescales, but Enceladus keeps it replenished, a perpetual source of fresh ice in the Saturnian system. Among those most deeply affected by the revelations about Enceladus was Carolyn Porco, the imaging team leader for the Cassini mission and one of the most prominent planetary scientists of her generation. Having witnessed the transformation of this small moon from obscure ice ball to one of the most promising environments for life beyond Earth, Porco became an eloquent advocate for future exploration of Enceladus. In her assessment, this moon offers something unique among all the worlds we know, a subsurface ocean that actively vents its contents into space, allowing a spacecraft to sample the waters of an alien sea without ever having to land, without having to drill through kilometers of ice, without confronting the enormous technical challenges that would attend exploration of similar oceans elsewhere. The plumes are, in effect, free samples, the interior of Enceladus offered up for analysis by any mission bold enough to fly through them. Porco has argued, with considerable scientific support, that Enceladus represents perhaps the best opportunity we have to search for extraterrestrial life in our own solar system, not because life is certain to exist there, but because the conditions appear potentially suitable and the means of investigation are comparatively accessible. The heat that drives all of this activity, the engine that maintains a liquid ocean and powers hydrothermal systems on a world far too small to retain primordial heat from its formation, derives primarily from tidal forces. Enceladus orbits Saturn in a gravitational resonance with the larger moon Dione, and this configuration causes its orbit to be slightly elliptical rather than perfectly circular. As Enceladus swings closer to and farther from Saturn along this elliptical path, the gravitational pull it experiences changes, flexing the moon's interior and generating friction that manifests as heat. This tidal heating is concentrated at the poles, particularly the South Pole, which explains why the tiger stripes and the most vigorous cryovolcanic activity occur in that region. The process has likely continued for much of the Moon's history, maintaining liquid water beneath the ice for hundreds of millions of years, perhaps longer, providing the stability that any developing life would require. And so Enceladus takes its place among the most remarkable objects in our solar system, a world where William Herschel's faint point of light has resolved into something approaching a laboratory for astrobiology, a natural experiment in the conditions that might give rise to and sustain life. The ocean beneath the ice is dark, cold in most places, subjected to pressures that would crush any unprotected human explorer, and yet at the hydrothermal vents on its floor, warmth and chemistry combine in ways that seem tantalizingly similar to the environments where life on Earth may have first emerged. Whether any organisms actually swim in those hidden waters, or cluster around those volcanic seeps, remains entirely unknown. The Cassini mission ended in 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere to prevent any possibility of contaminating the very moons it had studied so successfully, and no spacecraft has visited since. But the data returned from those extraordinary years of exploration continue to be analyzed, and plans for future missions are advanced and discussed and refined, because the small moon that William Herschel glimpsed in 1789 has revealed itself to be far more than anyone expected, a world of hidden complexity waiting patiently in the cold reaches of the outer solar system, its plumes rising silently into the darkness, carrying with them secrets that may take generations yet to fully understand. And so we come now to Io, the innermost of Jupiter's large moons, and perhaps the most extraordinary example of geological activity anywhere in our solar system, a world so restless and so continuously remade by its own internal fires that it stands apart from every other moon we have yet discussed, not as a frozen archive of ancient times, but as a body perpetually caught in the act of creating itself anew, turning itself inside out in a ceaseless display of volcanic fury that would seem almost impossible if we had not seen it with our own instruments, captured it in our photographs, and measured it with our patient, distant machines. Io is, quite simply, the most volcanically active body in the solar system, more active than Earth by a considerable margin, more active than any other moon or planet we have observed, with over 400 active volcanoes scattered across its surface at any given time, some of them erupting continuously for years or even decades, others flaring to life and subsiding in patterns we are still working to understand, all of them contributing to a landscape that is being constantly buried and rebuilt, erased and rewritten, in a process that has been ongoing for billions of years and shows no signs of slowing or stopping anytime soon. A world where the very concept of ancient terrain has no meaning because nothing on the surface is allowed to grow old. This remarkable character of Io was not always known to us, and indeed for centuries after Galileo first observed this moon through his modest telescope in 1610, Io remains simply one of 4 bright points of light accompanying Jupiter in its slow journey across the night sky, indistinguishable in its essential nature from its siblings Europa, Ganymede, and Callisto, all of them presumed to be cold, quiet, geologically dead worlds much like our own moon, interesting primarily for their orbital dance around the giant planet rather than for any intrinsic qualities of their own, and this assumption persisted largely unchallenged until the spring of 1979, when a spacecraft called Voyager 1 made its historic flyby of the Jovian system and everything we thought we knew about this small orange moon was suddenly and dramatically overturned. The discovery of active volcanism on Io came not during the closest approach of Voyager 1, when all attention was focused on capturing the highest resolution images possible, but rather in the days that followed, when a young navigation engineer named Linda Morabito was performing the routine but essential work of using images of Io and its background stars to calculate the precise position and trajectory of the spacecraft, work that required careful examination of the moon's limb, the curved edge where its surface meets the blackness of space, and it was during this examination, on March 9, 1979, that Morabito noticed something peculiar in one of the images, an anomalous crescent of brightness extending beyond the edge of the moon where no brightness should have been, a luminous arc that at first seemed like it might be another moon or perhaps some artifact of the imaging process, but which upon closer investigation revealed itself to be something far more extraordinary, a massive plume of material erupting from Io's surface and rising to an altitude of approximately 300 kilometers, vastly higher than any volcanic plume ever observed on Earth, frozen in the act of explosion against the dark backdrop of space. This first plume, ejected from a volcanic feature that would come to be known as Pele, named after the Hawaiian goddess of volcanoes, announced to the scientific community and to the world that Io was not a dead world at all but a furiously active one, and subsequent examination of the Voyager images revealed not just one but multiple active eruptions in progress, plumes rising from various points across the surface, dark spots marking the locations of recent lava flows, and a landscape utterly unlike anything seen elsewhere in the solar system, painted in startling shades of yellow and orange and red and white and black, a palette that spoke of sulfur in its many forms, deposited and redeposited across the surface by countless eruptions over countless years, creating a world that looks almost artificial in its vivid coloration, like something from a fever dream rather than a natural celestial body. Among the many volcanoes that dot Io's surface, one stands out as particularly remarkable, and that is Loki Patera, which holds the distinction of being the most powerful volcano in the entire solar system, not merely on Io but anywhere we have looked, a designation it earns through the sheer quantity of heat it radiates into space, heat that can be detected by infrared instruments from Earth orbit and from passing spacecraft, heat that speaks of an enormous reservoir of molten material. Churning just below the surface, a lava lake approximately 200 kilometers across, which is to say roughly the distance from London to Birmingham or from Los Angeles to San Diego, a vast cauldron of liquid rock whose surface periodically overturns as cooler material sinks and hotter material rises, creating waves of thermal emission that have been tracked over years and decades, allowing scientists to develop models of the lake's behavior that reveal it to be not a simple static pool, but a dynamic, living system with its own rhythms and its own internal logic. Loki Patera takes its name from the Norse god of fire and mischief, and one might say the name is appropriate, for this volcano has proven difficult to predict and full of surprises, sometimes appearing to follow regular patterns of brightening and dimming that suggest a periodic overturn of its lava surface, and sometimes deviating from those patterns in ways that remind us how much we still have to learn about the processes occurring within Io's tortured interior, processes that ultimately trace back not to radioactive decay, as on Earth, but to a completely different source of internal heat, one that depends upon Io's unique position in the Jovian system and its gravitational relationships with its neighboring moons. The explanation for Io's extraordinary volcanic activity lies in a phenomenon called tidal heating, which is perhaps best understood by first considering the tides on Earth, those daily rises and falls of our oceans caused by the gravitational pull of the moon and, to a lesser extent, the sun, pulls that create bulges in the ocean water and cause it to slosh back and forth as our planet rotates. And while we typically think of tides in terms of water, the solid body of the Earth also experiences tidal forces, flexing ever so slightly in response to the moon's gravity, rising and falling by perhaps 30 centimeters over the course of each day, a flexing so gentle and so gradual that we never notice it, but which nonetheless represents a continuous kneading of our planet's interior, a kneading that generates a small amount of heat through internal friction. Heat that is negligible compared to the heat produced by radioactive decay in Earth's core, but which demonstrates the principle that gravitational interaction can warm a planetary body. On Io, this same principle operates on a vastly larger scale, for Jupiter is not a modest-sized moon like our own, but a colossal planet with immense gravitational pull, and Io orbits not at the comfortable distance of the moon from Earth but much closer to its parent body, close enough that Jupiter's tidal forces raise bulges in Io's solid surface measuring as much as 100 meters high, compared to Earth's 30 centimeters. And furthermore, Io does not orbit Jupiter alone but in company with Europa and Ganymede, two other large moons whose gravitational influences prevent Io from settling into a perfectly circular orbit, forcing it instead to follow a slightly elliptical path that brings it closer to Jupiter at some times and farther away at others. And this variation in distance means that the tidal bulges are not constant but grow and shrink as Io orbits, flexing the moon's interior back and forth like a rubber ball being repeatedly squeezed and released. This flexing, this continuous kneading of Io's interior by the combined gravitational influences of Jupiter and its fellow moons, generates enormous amounts of heat through internal friction, far more heat than could be produced by radioactive decay alone. And this heat must go somewhere, and where it goes is up and out, melting the rock of Io's interior and driving it to the surface through hundreds of volcanic vents, creating the most volcanically active world we know, a world that is essentially being cooked from within by the same forces that create gentle ocean tides on Earth, forces that seem benign at human scales but which, multiplied by the mass of Jupiter and the resonant dance of the Galilean moons, become capable of melting an entire world. The orbital resonance that maintains this continuous heating is itself a remarkable phenomenon, for Io, Europa, and Ganymede have settled into a configuration where their orbital periods form simple ratios, with Io completing 4 orbits for every 2 orbits of Europa and every 1 orbit of Ganymede, a pattern called a Laplace resonance that keeps the 3 moons locked in a gravitational embrace, periodically tugging on each other in a predictable rhythm that prevents any of them from circularizing their orbits completely, ensuring that the tidal heating will continue indefinitely, or at least for as long as the orbital resonance persists, which by all calculations should be for billions of years to come. The heat generated by this process is immense, and the temperature variations across Io's surface are correspondingly extreme, ranging from approximately -130 degrees Celsius in regions far from active volcanism, where the surface has had time to radiate its heat away into the cold of space, to temperatures exceeding 1,600 degrees Celsius at active eruption sites, temperatures hot enough to melt almost any rock, hotter than the lavas typically erupted on Earth, suggesting that Io's volcanism involves not just ordinary basaltic magma but perhaps ultramafic lavas rich in magnesium and iron, lavas similar to those that erupted on Earth billions of years ago when our own planet was younger and hotter, making Io in some sense a window into Earth's geological past, a place where processes long since ceased on our world continue unabated. The colorful appearance of Io's surface, those striking yellows and oranges and reds that make it look almost like a celestial pizza in some of the Voyager and Galileo images, owes much to the element sulfur and its various compounds, for sulfur is abundant on Io and takes on different colors depending on its temperature and its molecular form, with yellow sulfur being the most common but red and orange and brown varieties also present, and these sulfurous materials are continuously deposited across the surface by volcanic eruptions, then buried by subsequent eruptions, then excavated and redeposited again, creating a complex layered stratigraphy that is never allowed to accumulate for long before being disrupted by the next volcanic event. This constant resurfacing has an interesting consequence for the study of Io, which is that there are essentially no impact craters visible on its surface, a remarkable absence given that impact craters are ubiquitous on nearly every other solid body in the solar system, from Mercury to the moons of Neptune. And their absence on Io tells us that the volcanic resurfacing rate is so high that any crater formed by an asteroid or comet impact is buried or erased within a geologically short time, perhaps a few thousand years or even less, meaning that the surface we see today is extraordinarily young by planetary standards, a surface that is being continuously renewed while we watch, or at least while our spacecraft watch on our behalf. Among the many individual volcanoes that have been studied on Io, Prometheus deserves particular mention for the curious behavior of its volcanic plume, which over the years between the Voyager flybys in 1979 and the Galileo mission in the 1990s was observed to have wandered across the surface by approximately 80 kilometers, not because the plume itself was drifting but because the volcanic vent feeding it was moving, or rather because new vents were opening at the leading edge of an advancing lava flow while old vents were shutting down behind, creating the impression of a plume that creeps slowly across the landscape like a garden sprinkler being dragged across a lawn, a phenomenon that illustrates how active and how dynamic Io's volcanic systems truly are. Another notable volcanic feature is Tvashta, located in Io's polar regions, which provided one of the most spectacular observations of Io's volcanism when the New Horizons spacecraft flew past Jupiter in early 2007 on its way to Pluto and observed an enormous eruption in progress, a plume rising some 330 kilometers above the surface, beautifully backlit by the sun and captured in stunning detail by the spacecraft's cameras, a farewell gift from the Jovian system to a spacecraft that would not reach its ultimate destination for another 8 years, and a reminder that Io's volcanoes continue their work regardless of whether anyone is watching. Io possesses an atmosphere, though to call it an atmosphere in the same sense as Earth's would be misleading, for it is an extraordinarily thin and tenuous envelope of gas, composed primarily of sulfur dioxide with traces of other sulfur compounds, an atmosphere so thin that its surface pressure is less than a billionth of Earth's sea level pressure, barely an atmosphere at all by terrestrial standards. And yet it is sufficient to be detected and studied, and it exhibits a remarkable behavior. Related to Io's position relative to Jupiter, for when Io passes into Jupiter's shadow and is eclipsed from the Sun's warming rays, the temperature of its surface drops rapidly, and as it drops, the sulfur dioxide that forms the bulk of the atmosphere begins to freeze out, condensing onto the surface as frost, causing the atmosphere to partially collapse, only to reform when Io emerges from eclipse and the sulfur dioxide sublimates once again, a daily rhythm of atmospheric expansion and contraction that has no parallel elsewhere in the solar system. And so Io continues its endless dance around Jupiter, locked in resonance with its fellow moons, heated from within by tidal forces, erupting continuously from hundreds of volcanic vents, painting and repainting its surface in shades of sulfur yellow and volcanic black, a world that might seem hellish by any human standard but which is simply following the physical laws that govern all matter and energy, turning itself inside out not from any malice or chaos but from the simple mechanical consequence of gravity and friction and heat, a demonstration on a planetary scale that worlds need not be static and dead, that geological activity can arise from sources other than radioactive decay, and that the universe contains wonders we could never have predicted until we sent our small machines out to look, and having looked, to send back their patient observations for us to study and to marvel at, quietly, from the comfort of our own small world. In the outer reaches of our solar system, far beyond the familiar orbits of the giant planets, there exists a small world that was once considered the ninth planet, and beside it, keeping eternal company through the long cold centuries, orbits a moon so substantial in proportion to its parent body that astronomers have come to regard the pair as something quite special, a true binary system dancing together through the darkness. And this companion, this faithful attendant to distant Pluto, is called Charon, and its story begins not in the frozen depths of the Kuiper Belt but rather in a quiet observatory in the high desert of northern Arizona, where a patient astronomer noticed something peculiar in a photograph, something that would change our understanding of Pluto forever. The year was 1978, and James Christie was working at the United States Naval Observatory's Flagstaff Station, which sits at an elevation of more than 2,000 meters among the ponderosa pines, where the air is thin and clear and the scene conditions allow for careful astronomical work. And on the 22nd of June of that year, Christie was examining photographic plates of Pluto that had been taken for the purpose of refining the small world's orbit, a routine task that required measuring the precise position of Pluto against the background stars, and as he studied the images, he noticed something that might have been dismissed by a less attentive observer, for the image of Pluto appeared slightly elongated, as though the tiny point of light had been stretched or smeared during the exposure, and at first this might have seemed like nothing more than a flaw in the photographic process, perhaps a slight tracking error or an imperfection in the emulsion. But Christie was thorough in his methods, and he noticed that the background stars in the same images appeared perfectly round and sharp, which meant that the elongation was not an artifact of the telescope's motion or the photographic process but was instead something inherent to Pluto itself. Christie began to examine older photographic plates from the observatory's archives, images that had been taken over the preceding years, and he found that this elongation appeared in multiple photographs, and moreover, the direction of the elongation changed over time in a regular and predictable pattern, as though something were orbiting Pluto and causing the combined light of two objects to blur together into that characteristic stretched shape, and with careful analysis, Christie determined that this unseen companion completed one orbit around Pluto approximately every 6 1/3 days, and he had discovered a moon, the first and largest moon of Pluto, though it would be many years before anyone could see it clearly as a separate world. When it came time to name this newly discovered moon, Christie followed the convention of drawing from Greek and Roman mythology, as is traditional for objects in our solar system, and the name Charon was particularly fitting, for in classical mythology Charon was the ferryman who carried the souls of the deceased across the river Styx to the underworld, which was the realm of Hades, and the Romans called this same underworld deity Pluto, so it seemed entirely appropriate that Pluto's moon should be named for the boatman who served the god of the underworld, and there was also a personal dimension to this choice, for the first syllable of Charon could be pronounced to sound like the beginning of Charlene, which was the name of James Christie's wife, and so this distant moon carries within its name both the weight of ancient mythology and a quiet tribute to the astronomer's companion here on Earth. For nearly 4 decades after its discovery, Charon remained little more than a point of light beside Pluto, its surface features completely unknown, its geology a matter of speculation, and even the Hubble Space Telescope, powerful as it is, could show the pair only as fuzzy blobs of pixels, though these observations were enough to reveal that Charon's surface appeared grayish in color, quite different from the reddish tones of Pluto, and astronomers could measure the moon's size and orbit with increasing precision, and they could determine that Charon was remarkably large compared to Pluto, but the details of its surface remained hidden by the sheer distance involved, for Pluto and Charon orbit the Sun at an average distance of nearly 40 times the Earth-Sun distance, so far away that sunlight reaching them is almost 1,000 times fainter than the sunlight we experience on a summer afternoon. The relationship between Pluto and Charon is unlike that of any other planet and moon pairing in our solar system, for Charon is approximately 12% of Pluto's mass, which is an extraordinarily high ratio, and to put this in perspective, our own moon is only about 1.25% of Earth's mass, and even that makes the Earth-Moon system unusual among the terrestrial planets. But the Pluto-Charon system takes this to an entirely different level, and because Charon is so massive relative to Pluto, something quite interesting happens with their gravitational interaction, for when two bodies orbit each other, they actually both orbit around their common center of mass, which astronomers call the barycenter, and in most planet-moon systems, this barycenter lies well within the larger body, often quite close to its center, so that the planet appears to wobble only slightly while the moon does most of the moving. But in the Pluto-Charon system, the barycenter lies outside of Pluto's surface entirely, suspended in the empty space between the two worlds, which means that both Pluto and Charon orbit around a point in space that neither body contains, and this is what qualifies them as a true binary system, two worlds locked together in an endless gravitational embrace, neither one strictly dominant over the other. This gravitational connection has led to another remarkable feature of the Pluto-Charon system, which is their state of mutual tidal locking, and to understand what this means, consider that our own moon is tidally locked to Earth, meaning that the moon rotates on its axis in exactly the same time that it takes to complete one orbit around Earth, which is why we always see the same face of the moon and never the far side. But Earth is not tidally locked to the moon, so from the moon's perspective, Earth appears to rotate through its full cycle of day and night, but in the Pluto-Charon system, both bodies are tidally locked to each other, which means that Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto, and both their rotation periods and their orbital period are identical, approximately 6.4 Earth days. So if you were standing on the Pluto-facing side of Charon, Pluto would hang motionless in your sky, never rising and never setting, always occupying the same position among the stars, while if you were standing on the opposite hemisphere of Charon, you would never see Pluto at all, and the same is true in reverse for observers on Pluto, and this mutual synchronization is the inevitable result of billions of years of tidal interaction between two closely orbiting bodies of comparable size. Everything changed on the 14th of July, 2015, when NASA's New Horizons spacecraft swept through the Pluto system at a velocity of nearly 14 kilometers per second, too fast to slow down and enter orbit, but moving at just the right trajectory to capture detailed images and scientific measurements during its brief encounter. And the images that New Horizons sent back to Earth transformed Charon from a fuzzy blob into a real place, a world with mountains and canyons and plains, with its own geological history written across its surface in the language of craters and cracks and smooth resurfaced terrain. One of the most striking features revealed by New Horizons was the large reddish-brown region covering Charon's north polar area, a feature so distinctive that the mission scientists informally named it Mordor Macula, borrowing from the Darkland in Tolkien's fictional Middle-earth, and macula being the Latin term for spot or stain, and this ruddy polar cap is quite different in color from the rest of Charon's surface, which is predominantly gray, and the explanation for this color difference involves a complex and rather elegant process of atmospheric chemistry that connects Charon to its larger companion Pluto. Pluto, despite its small size and frigid temperatures, possesses a thin atmosphere composed primarily of nitrogen gas, with small amounts of methane and carbon monoxide, and this atmosphere is slowly escaping into space, leaking away from Pluto's weak gravitational hold, and some of this escaping gas, particularly the methane, finds its way to Charon, where it becomes trapped in the extremely cold polar regions during Charon's long winter. For like Earth, the Pluto-Charon system has seasons. Caused by the tilt of its rotational axis, and during the winter at each pole, temperatures drop even further than the already frigid baseline, cold enough to freeze the methane molecules that have drifted across from Pluto's escaping atmosphere, and these frozen methane deposits are then exposed to ultraviolet radiation from the distant sun and to cosmic rays from interstellar space. And this radiation triggers chemical reactions that transform the simple methane molecules into more complex organic compounds called tholins, which are reddish-brown in color. And as the seasons change and the pole emerges from its decades-long winter, the lighter volatile compounds sublimate away, returning to vapor and escaping back into space, but the heavier tholin compounds remain behind, painting the polar region with that distinctive rusty hue, and this process has been occurring for billions of years, gradually building up the layer of organic material that gives Mordor Macula its appearance. The surface of Charon also bears witness to tremendous tectonic forces that must have been active early in the Moon's history, for New Horizons revealed an extensive system of canyons, troughs, and scarps stretching across much of the visible surface, and the largest of these features has been named Serenity Chasma, a vast rift valley that extends for hundreds of kilometers and reaches depths of up to 9 kilometers in some places, which is approximately twice the depth of the Grand Canyon. Here on Earth, and the Grand Canyon is itself one of the most impressive geological features on our planet, carved over millions of years by the Colorado River, but Serenity Chasma was not formed by flowing water, for there is no liquid water on Charon's surface, where temperatures hover around -220 degrees Celsius, cold enough that water ice is as hard and rigid as rock. Instead, these enormous canyons are thought to have formed through a process related to the freezing of a subsurface ocean, for planetary scientists believe that early in its history, Charon may have possessed a liquid water ocean beneath its icy crust, kept warm by the residual heat of formation and perhaps by tidal heating from its gravitational interaction with Pluto, and as this internal ocean gradually cooled and froze over the eons, something interesting would have happened, because water is unusual among substances in that it expands when it freezes, unlike most materials which contract as they solidify, and as the subsurface ocean froze and expanded, it would have put tremendous pressure on the outer icy shell of Charon, and eventually this pressure would have caused the surface to crack and split, creating the vast canyon systems we see today. And so these chasms are essentially stretch marks on Charon's surface, evidence of a world that quite literally outgrew its own skin. In the southern hemisphere of the Encounter Hemisphere, the side of Charon that New Horizons was able to image in detail, there is a region that appears remarkably different from the heavily cratered and tectonically fractured terrain that dominates much of the surface, and this region has been named Vulcan Planitia, after the Roman god of fire and the forge, and it presents a relatively smooth and gently rolling plain with far fewer impact craters than the surrounding areas, which suggests that this terrain is geologically younger, that something happened here after the period of heavy bombardment that created the craters elsewhere on Charon's surface, and the leading explanation is that Vulcan Planitia was resurfaced by cryovolcanism, which is a type of volcanism that occurs on icy worlds where the magma is not molten rock but rather slushy mixtures of water, ammonia, and other volatile compounds. In cryovolcanism, these icy slurries erupt onto the surface much as lava flows from volcanoes on Earth, spreading out and eventually freezing solid, covering over whatever terrain existed before, including any impact craters, and the relative smoothness of Vulcan Planitia and its lower crater count suggest that such cryovolcanic activity occurred here sometime in Charon's past, perhaps billions of years ago when the Moon's interior was still warm enough to sustain such processes, and the flow-like features and what appear to be cryovolcanic domes visible in the New Horizons images support this interpretation, painting a picture of Charon as a world that was once more geologically active than its current frozen appearance might suggest. The surface composition of Charon is dominated by water ice, which forms the bedrock of this frozen world, but spectroscopic observations have also revealed the presence of ammonia hydrates on the surface, which is significant because ammonia exposed to the harsh radiation environment of the outer solar system should break down relatively quickly in geological terms, and its presence suggests that there may be ongoing processes that bring fresh ammonia-bearing material to the surface, perhaps through continued cryovolcanic venting or through impact gardening of subsurface materials. And this adds another layer of complexity to our understanding of this distant moon. Charon is roughly 1,200 kilometers in diameter, making it about half the size of Pluto, and it orbits at a distance of approximately 19,570 kilometers from Pluto's center, close enough that from Pluto's surface Charon would appear about 7 times larger in the sky than our full moon appears from Earth, a substantial presence hanging motionless in the heavens for those on the Pluto-facing hemisphere. And from Charon, Pluto would appear even larger, nearly 8 times the apparent diameter of Earth's moon as seen from our world, dominating the sky with its heart-shaped nitrogen ice plains and its reddish tholin-coated highlands clearly visible to the naked eye. The discovery and subsequent exploration of Charon has revealed it to be a world of contrasts, with its grey icy surface and its red polar cap, its ancient heavily cratered highlands and its smooth cryovolcanic plains, its tremendous canyon system speaking of internal forces that reshaped the moon long ago. And through it all, Charon continues its slow gravitational waltz with Pluto, 2 worlds forever facing each other across 19,000 kilometers of space, locked together in their journey around the distant sun, a journey that takes 248 Earth years to complete. And if you find yourself growing drowsy as you contemplate this faithful companion to the former 9th planet, that is entirely natural, for the universe is vast and patient and full of quiet wonders that ask nothing of us but our peaceful attention, and Charon will continue its orbit whether we are awake or asleep, turning its red-capped pole toward the sun and away again as the long seasons of the outer solar system proceed at their unhurried pace. In the year 1877, during a particularly favorable opposition of Mars, when the red planet drew closer to Earth than it had in many years, an American astronomer named Asaph Hall sat patiently at the Great Refractor Telescope of the United States Naval Observatory in Washington, and there, through long nights of careful watching, he discovered the 2 small moons that circle our neighboring world. The opposition of that year brought Mars within a mere 56 million kilometers of Earth, and Hall, who had been searching methodically for any satellites that might exist, nearly abandoned his efforts in the humid August heat, but his wife Angelina encouraged him to continue for just a few more nights, and so he did. And on the 12th of August he noticed a tiny point of light that seemed to move with Mars against the background stars. 6 nights later, on the 18th of August, he found a second moon, even closer to the planet, and thus Pharbas and Deimos entered the catalogues of known worlds, named for the mythological sons of Ars, the Greek god of war, one representing fear and the other terror, though there is nothing terrifying about these small bodies when one comes to know them as they truly are, which is to say irregular lumps of ancient rock tumbling through the darkness in their endless circuits around the rusty plains of Mars. What makes this discovery particularly curious, and what has delighted readers of literature and astronomy alike for many generations, is that the satirist Jonathan Swift, writing his famous novel Gulliver's Travels in 1726, described 2 moons orbiting Mars a full 151 years before Asaph Hall ever turned his telescope toward the red planet. In the 3rd voyage of that book, when Gulliver visits the flying island of Laputa, whose inhabitants are devoted to mathematics and astronomy to the exclusion of all practical matters, Swift wrote that their astronomers had discovered 2 lesser stars, or satellites, which revolve about Mars, whereof the innermost is distant from the center of the primary planet exactly 3 of his diameters, and the outermost 5, the former revolving in the space of 10 hours, and the latter in 21 and a half. It is quite remarkable, when one considers it quietly, that Swift placed his fictional moons in orbits that bear some resemblance to the actual orbits of Pharbas and Deimos, though his estimates were not precisely correct, and there is no evidence that he possessed any special knowledge or that this was anything more than a fortunate guess, perhaps based on the pattern that Jupiter was known to have 4 moons and Earth had 1, so Mars, being between them, might reasonably have 2. The French philosopher Voltaire also mentioned 2 Martian moons in his story Micromegas, published in 1752, and so the idea had some currency among literary figures of the Enlightenment, though it would wait more than a century for confirmation by Hall and his 26-inch refractor on those warm August nights. Pharbas, the larger and inner moon, measures approximately 27 kilometers by 22 kilometers by 18 kilometers, which is to say it is not spherical at all but rather shaped somewhat like a lumpy potato or a worn river stone, and it orbits Mars at a distance of only 9,376 kilometers from the planet center, which places it closer to its parent body than any other known moon in our solar system. This proximity means that Pharbas completes one orbit in just 7 hours and 39 minutes, and because Mars rotates on its axis once every 24 hours and 37 minutes, the moon actually travels around the planet faster than the planet spins beneath it. If you were standing on the Martian surface and watching Pharbas rise, you would see it appear in the west rather than the east, cross the sky in about 4 hours and 15 minutes, and set in the east, which is quite the opposite of what we observe when watching our own moon from Earth. An observer on Mars might see Pharbas rise and set twice in a single Martian day, a strange and restless companion that never stays long in the sky. This peculiar orbital arrangement, with the moon orbiting faster than the planet rotates, has consequences that unfold very slowly over millions of years, and these consequences are not favorable for Pharbas. Because the moon moves faster than the surface below it, the tidal bulge that Pharbas raises on Mars tends to lag behind the moon's position, and this creates a gravitational interaction that gradually transfers energy from Pharbas's orbit to Mars's rotation. The result is that Pharbas spirals inward toward Mars at a rate of approximately 1.8 centimeters per year, which seems almost immeasurably small but which accumulates over geological time into a significant change. In roughly 50 million years, give or take, Pharbas will either crash into the Martian surface or, more likely, be torn apart by tidal forces once it crosses inside the Roche limit, the distance at which the planet's gravitational pull overcomes the moon's own structural integrity. When this happens, the fragments of Pharbas may form a ring around Mars, a temporary adornment that will itself eventually rain down upon the planet, and so this small moon is doomed, though its doom is so far in the future that countless generations of life on Earth will come and go before Pharbas meets its end, and there is no urgency in this knowledge, only a quiet recognition of the long processes that shape our solar system. The surface of Pharbas is dominated by a single enormous impact crater named Stickney, after Angeline Stickney Hall, the wife of Asaph Hall, who encouraged him to continue his search on those summer nights in 1877. The Stickney crater measures approximately 9 kilometers in diameter, which is nearly half the mean diameter of Pharbas itself, and when one considers the violence of the impact that created this scar, it becomes clear that Pharbas very nearly did not survive the collision. The impactor that struck Pharbas and excavated the Stickney crater must have come close to shattering the small moon entirely, and computer simulations suggest that the impact would have sent shock waves reverberating through the interior, creating fractures that extend throughout much of the body. That Pharbas remains whole today is somewhat remarkable, and one might imagine, if one were inclined to such thoughts while drifting towards sleep, that this battered little moon has been through a great deal in its long existence, and yet it continues its patient circling of Mars, grooved and cratered but still intact. Speaking of grooves, the surface of Pharbas is marked by a curious network of parallel lines, shallow troughs that stretch across the moon's surface in patterns that have puzzled planetary scientists for decades. These grooves are typically 100 to 200 meters wide and 10 to 30 meters deep, and they extend for kilometers across the terrain, giving portions of Pharbas the appearance of a scored and scratched stone. Several explanations have been proposed for these features, and the mystery has not been entirely resolved. One hypothesis suggests that the grooves are fractures caused by tidal stresses, as Mars's gravity pulls on Pharbas with varying intensity depending on the moon's orientation and position in its orbit, and over billions of years these flexing forces might have cracked the surface in systematic ways. Another explanation proposes that the grooves are chains of secondary craters, formed when debris ejected from the Stickney impact fell back onto the surface in linear patterns. Yet another idea suggests that the grooves are related to the rolling of boulders across the surface following the Stickney impact, though this seems less widely accepted. More recent studies have proposed that the grooves might be signs of ongoing structural failure, evidence that Farbas is slowly being pulled apart by tidal forces as it spirals ever closer to Mars. And if this interpretation is correct, the grooves may be a harbinger of the Moon's eventual destruction, though that destruction remains tens of millions of years away. Deimos, the smaller and outer Moon, orbits Mars at a distance of approximately 23,460 kilometers, completing one circuit in about 30 hours and 18 minutes. It measures roughly 15 kilometers by 12 kilometers by 11 kilometers, making it even more irregularly shaped than its companion, and its surface is notably smoother than that of Farbas, lacking the dramatic grooves and large craters that characterize the inner Moon. The largest crater on Deimos, named Swift in honor of the author who imagined Martian moons before they were found, measures only about 3 kilometers across. The smoothness of Deimos is thought to result from a layer of regolith, loose soil, and dust that has gradually filled in smaller craters and softened the terrain over billions of years. From the surface of Mars, Deimos would appear as a bright star-like point, crossing the sky slowly from east to west over the course of about 2.5 days, occasionally eclipsing the Sun but producing only a small dark spot rather than a dramatic total eclipse, more of a transit than a true obscuration. The question of where Farbas and Deimos came from has occupied planetary scientists for many years, and two main hypotheses have emerged, neither of which has been definitively confirmed. The first hypothesis suggests that the moons are captured asteroids, objects that originated in the asteroid belt between Mars and Jupiter and that wandered close enough to Mars to be trapped by its gravity. This idea is supported by the fact that both moons have reflectance spectra similar to certain types of asteroids, particularly carbonaceous chondrites, which are primitive rocky bodies rich in carbon compounds. However, capturing an asteroid into a stable, circular, equatorial orbit is dynamically difficult, and the present orbits of Farbas and Deimos are remarkably circular and aligned with the Martian equator, which would be unusual if they were simply plucked from passing trajectories. The second hypothesis proposes that Farbas and Deimos formed from debris ejected into orbit around Mars following a giant impact on the planet's surface, similar to the way our own Moon is thought to have formed from debris created when a Mars-sized body struck the early Earth. This model can more easily explain the circular, equatorial orbits of the moons, but it raises questions about their composition, since material ejected from Mars might be expected to show more similarity to Martian rocks than to asteroid material. Some researchers have suggested that both hypotheses might contain elements of truth. Perhaps the moons formed from a mixture of impactor material and Martian debris, or perhaps they are captured objects whose orbits were subsequently circularized by tidal interactions over billions of years. Resolving this question will require detailed analysis of samples from the moons themselves, which leads us to the topic of spacecraft missions. The Soviet Union attempted to explore Farbas with a pair of spacecraft launched in 1988, known as Farbas 1 and Farbas 2, but both missions encountered difficulties that prevented them from completing their objectives. Farbas 1 was lost during its cruise to Mars in September 1988 when an incorrect command was sent to the spacecraft, disabling its attitude control system and leaving it tumbling and unable to point its solar panels toward the Sun. Farbas 2 reached Mars and entered orbit successfully in January 1989, returning images and data about both Mars and its moons. But contact was lost in March of that year just as the spacecraft was approaching within 200 kilometers of Farbas for close observations and a planned landing of two small surface stations. The cause of the failure was determined to be a malfunction in the onboard computer system, and so the ambitious Soviet program ended without achieving its primary goals, though the data it did return contributed to our understanding of the Martian system. Looking toward the future, the Japan Aerospace Exploration Agency is developing a mission called MMX, which stands for Martian Moons Exploration, with a planned launch in 2026. This spacecraft will study both Farbas and Deimos from orbit and will land on Farbas to collect samples of the surface material, approximately 10 grams of regolith, which will then be returned to Earth for laboratory analysis sometime in the early 2030s if all goes according to plan. The analysis of these samples may finally resolve the question of the Moon's origins, determining whether they are indeed captured asteroids, impact debris from Mars, or something else entirely. Until that time, Farbas and Diamos will continue their quiet journeys around Mars, one spiraling slowly inward toward its eventual destruction, the other drifting gradually outward, two small, dark, potato-shaped worlds that have orbited the red planet since long before any telescope was turned toward the sky, and will continue to do so for millions of years yet, patient and unhurried in their ancient rounds. Miranda is the smallest of Uranus's 5 major moons, a diminutive world measuring just 472 kilometers across, which means you could fit it quite comfortably within the borders of a modest country. And yet this tiny moon possesses what many planetary scientists consider to be the most bewildering and varied landscape of any body in our solar system. It was discovered in the year 1948 by Gerard Kuiper, a Dutch-American astronomer working at the McDonald Observatory in Texas, who spotted a faint pinprick of light moving against the fixed stars in the vicinity of Uranus, and he named this new moon after the daughter of the magician Prospero in William Shakespeare's play The Tempest, a tradition that would come to define all of the moons orbiting that distant ice giant. At the time of its discovery, Miranda was little more than a speck, a point of light whose secrets would remain hidden for nearly 4 decades, and no one could have guessed what extraordinary revelations awaited when a spacecraft would finally journey close enough to see its surface in detail. That moment came on the 24th of January, 1986, when the Voyager 2 spacecraft swept past the Uranian system during its grand tour of the outer planets, and although the flyby was relatively brief, lasting only a matter of hours in terms of useful observation time, the images that were transmitted back to Earth across billions of kilometers of empty space caused considerable astonishment among the scientific community. The pictures revealed a moon that seemed, at first glance, to make very little sense, a patchwork world where ancient, heavily cratered terrain sits directly adjacent to vast regions of young, grooved landscape, as though someone had taken pieces from several different moons and assembled them together without particular regard for continuity or geological consistency. This striking appearance earned Miranda an informal nickname that has persisted in popular descriptions ever since, though of course the moon itself remains indifferent to such terrestrial literary references. The surface of Miranda presents a study in contrasts that you might find gently puzzling if you were to examine the Voyager images closely, which you need not do now, but it is pleasant to imagine them nonetheless. There are regions that appear ancient and battered, pockmarked with impact craters accumulated over eons of exposure to the debris drifting through the outer solar system, and these areas look much as you might expect a small, cold moon to appear, frozen and static and bearing the scars of countless collisions. But then, without warning or gradual transition, these old cratered plains give way to entirely different terrain, younger surfaces marked by intricate patterns of ridges and grooves that suggest geological activity of a sort that seems almost impossible on such a small and presumably cold world. The boundary between these different terrains can be remarkably sharp, as though drawn with a ruler, and this juxtaposition of old and young, quiet and active, represents one of Miranda's most enduring mysteries. The most striking features on Miranda are 3 large formations that planetary scientists call coronae, a term borrowed from the Latin word for crown, though these features bear little resemblance to any crown you might picture in your mind. Each corona is a roughly oval region, tens to hundreds of kilometers across, characterized by complex patterns of concentric ridges and grooves that give them a distinctive appearance quite unlike anything seen elsewhere in the solar system at that time. The 3 coronae have been named Arden, Elsinore, and Inverness, continuing the Shakespearean tradition that Gerard Kuiper began with the moon itself, for Arden refers to the forest in As You Like It, Elsinore is the Danish castle from Hamlet, and Inverness is of course the Scottish seat where dark deeds unfold in Macbeth. These names lend an unexpected literary quality to discussions of Mirandan geology, though the features themselves care nothing for human drama or poetry. Arden Corona occupies a substantial portion of Miranda's surface and displays a pattern of ridges that curve and wind across its interior in a manner that some observers have likened to racetracks, concentric ovals nested within one another like the lanes of an athletic stadium viewed from high above. These features suggest that some process once shaped the surface here in a systematic way, perhaps through the slow upwelling of warmer material from below or the gradual relaxation of the crust over geological time, though the precise mechanism remains a subject of scientific discussion. Elsinore Corona presents a somewhat different character, with its own system of ridges and a slightly different overall texture, while Inverness corona, which Voyager 2 imaged particularly well, shows perhaps the most dramatic example of the racetrack pattern, with bright and dark bands alternating in sweeping curves that seem almost deliberate in their regularity. It is worth pausing here to consider what the word cryovolcanism means, for it appears frequently in discussions of Miranda and other icy moons, and understanding it may help you appreciate the geological processes that might have shaped these unusual landscapes, though you may also find your thoughts drifting pleasantly elsewhere, which is perfectly acceptable. On Earth, we are familiar with volcanism involving molten rock, magma rising from the planet's interior to erupt at the surface as lava. But on the frozen moons of the outer solar system, where temperatures plunge to hundreds of degrees below zero, water ice behaves much as rock does on Earth, forming a rigid crust, while mixtures of water, ammonia, and other volatile compounds can behave as the equivalent of magma, remaining liquid at temperatures that would freeze pure water solid. When these cold liquids rise toward the surface and erupt, the process is called cryovolcanism, or ice volcanism, and it may have played a significant role in creating the groove terrains we see on Miranda today. Perhaps the most celebrated feature on Miranda, and certainly the one that captures the imagination most readily, is a great cliff known as Verona Rupes, named after the Italian city that serves as the setting for Romeo and Juliet. This towering escarpment rises approximately 20 kilometers from base to top, making it the tallest known cliff in the entire solar system, a distinction that sounds dramatic but which we shall consider in a calm and measured way. To put this height in perspective, you might recall that Mount Everest rises roughly 9 kilometers above sea level, so Verona Rupes is more than twice as tall as the highest point on Earth, though of course comparing a cliff to a mountain is not entirely straightforward and the figures depend somewhat on how one measures such things. What makes Verona Rupes particularly interesting, in a gentle and unhurried way, is what would happen if you were to step off its edge. Not that anyone is suggesting you should, but as a thought experiment it illuminates something important about Miranda's nature. The Moon is so small, and its gravitational pull consequently so weak, that an object falling from the top of the cliff would take approximately 12 minutes to reach the bottom. This is because Miranda's surface gravity is only about 8/1000ths of what we experience on Earth, so while the cliff is enormously tall, the leisurely pace of falling in such weak gravity means the descent would be surprisingly gentle in terms of final impact velocity, perhaps comparable to a modest car crash rather than the obliterating collision you might expect from such a tremendous height. This curious fact tells us something about the relationship between size, gravity, and the experience of vertical distance that we perhaps take for granted on our much larger world. The origin of Verona Rupes is not entirely understood, but it appears to be a fault scarp, a feature created when one block of crust drops downward relative to another along a fracture, and such faulting might be related to the same internal processes that created the coronae. Some scientists have suggested that Miranda experienced episodes of tidal heating in its past, when gravitational interactions with Uranus and perhaps other moons generated friction within the moon's interior, warming it enough to drive geological activity. This heating would not have been constant but might have occurred during periods when Miranda's orbit brought it into resonance with other moons, a topic we shall touch upon shortly. There are two principal theories that attempt to explain Miranda's extraordinary appearance, and while neither has been definitively proven, both offer plausible mechanisms for creating such a jumbled and diverse surface. The first theory suggests that Miranda was catastrophically disrupted at some point in its history, shattered by a massive impact into numerous fragments that subsequently reaccumulated under their mutual gravity, reassembling into a single body but in a disordered configuration that mixed materials from different depths. In this scenario, the coronae might represent regions where denser material that was once deep within Miranda's interior ended up near the surface, while other areas retained their original ancient crust. The process would be rather like breaking a vase and gluing it back together, except without any glue and relying entirely on gravity, and without anyone intending it to happen. The second theory proposes that Miranda was never disrupted but instead experienced incomplete differentiation, meaning that the process by which heavier materials sink toward the center of a planetary body and lighter materials rise toward the surface was interrupted before it could finish. In this view, the coronae represent areas where dense material was in the process of sinking downward, or perhaps rising upward in the form of cold, sluggish plumes of ice, when the internal heat source failed and the whole process ground to a halt. The cryovolcanic resurfacing that accompanied this partial differentiation would have created the groove terrains, while the ancient cratered regions are simply areas that were never affected by the upwelling. This theory has the advantage of not requiring a catastrophic impact, though it does require that Miranda once had a heat source capable of driving internal convection. Miranda's orbit around Uranus presents another gentle puzzle, for it is inclined at an angle of 4.2 degrees relative to the equatorial plane of the planet, which is unusual because the gravitational influence of the flattened Uranus should tend to pull moons into orbits aligned with the equator over time. This orbital anomaly suggests that something disturbed Miranda's orbit in the past, and the most likely explanation involves an orbital resonance with Umbriel, another of Uranus's major moons. An orbital resonance occurs when two bodies exert regular gravitational tugs on each other at predictable intervals because their orbital periods are related by a simple ratio, and these repeated tugs can pump up orbital eccentricity or inclination over time. If Miranda and Umbriel were once locked in such a resonance, the gravitational interaction could have gradually tilted Miranda's orbit, while also generating the tidal heating that might have driven its geological activity. Eventually, Miranda would have escaped from the resonance, but the elevated inclination and the surface features would remain as evidence of that ancient gravitational dance. The idea that a moon's geology could be driven by its orbital history, by the subtle gravitational waltz it performs with its siblings, is one of the more elegant concepts in planetary science, and Miranda serves as a compelling example of how even small worlds can harbor complex histories. The energy required to reshape a moon's surface need not come from radioactive decay alone, as it does primarily on Earth, but can be borrowed from the gravitational potential of the entire orbital system, converted through tidal flexing into the heat that drives cryovolcanism and tectonics. This same process operates more dramatically on Jupiter's moon Io and on Saturn's moon Enceladus, but Miranda reminds us that even the moons of distant Uranus are not immune to such dynamic behavior. As you rest now, perhaps picturing this small grey moon tumbling slowly through the darkness beyond Saturn, you might find it comforting to know that Miranda continues its patient orbit around Uranus, completing one circuit approximately every 1.4 Earth days, turning the same face toward its planet just as our own moon keeps one face toward Earth. The great cliff of Verona Rupe stands in silence, its shadow stretching across the ancient ice, and the coronae bear their concentric patterns like fingerprints of geological processes that operated hundreds of millions or billions of years ago and then fell quiet. No spacecraft has visited the Uranian system since Voyager 2 passed through in 1986, and so our knowledge of Miranda remains frozen in time, captured in those images transmitted across the solar system nearly 4 decades ago, waiting for a future mission that may one day return to reveal what further secrets this peculiar moon might hold. Ganymede and Callisto are two worlds that orbit the same planet, formed from the same swirling disk of material, and yet they have become remarkably different places over the 4.5 billion years since their creation. They are often described as twin giants because they are similar in size and composition, both being vast spheres of rock and ice circling Jupiter in the cold outer reaches of our solar system. And yet, despite these similarities, one has remained geologically active for much of its history, developing a complex internal structure and even generating its own magnetic field, while the other has remained largely unchanged since the earliest days of the solar system, its ancient surface preserving a record of countless impacts from a time when the solar system was a far more chaotic place. This difference between two seemingly similar worlds is one of the gentle mysteries of planetary science, and understanding why they evolved so differently tells us something quite fundamental about how energy and heat shape the destinies of celestial bodies. Let us begin with Ganymede, because it holds a special distinction among all the moons that orbit all the planets in our solar system. Ganymede is the largest moon anywhere, a world with a diameter of approximately 5,268 kilometers, which makes it larger than the planet Mercury. If Ganymede orbited the Sun directly rather than circling Jupiter, we would almost certainly classify it as a planet in its own right, because it is a substantial world with a complex interior and an atmosphere of its own, thin though that atmosphere may be. Mercury, by comparison, has a diameter of about 4,880 kilometers, so Ganymede exceeds it by several hundred kilometers, and yet Ganymede contains only about 45% of Mercury's mass, because Ganymede is composed largely of water ice mixed with rock, whereas Mercury is dense with iron and silicate materials. This difference in composition is a reminder that size alone does not determine the character of a world, and that the materials from which a body forms and the conditions under which it forms leave lasting impressions on its nature. When the Galileo spacecraft arrived at Jupiter in December of 1995 and began its extended mission studying the giant planet and its moons, it made numerous discoveries that transformed our understanding of this miniature solar system. Among the most surprising of these discoveries was announced in 1996, when scientists determined that Ganymede possesses its own intrinsic magnetic field, meaning that the Moon generates a magnetic field from within itself rather than simply responding to the powerful magnetic field of Jupiter. This made Ganymede unique among all the moons in our solar system, because no other moon is known to generate its own magnetic field in this way. The Earth generates its magnetic field through the movement of molten iron in its outer core, a process called a dynamo, and the presence of a magnetic field at Ganymede suggested that something similar might be occurring within this distant moon, that there might be a core of iron or iron sulfide that remains at least partially molten and in motion, creating electrical currents that generate the observed magnetic field. The existence of this magnetic field told scientists that Ganymede must have a differentiated interior, meaning that the materials within the moon have separated into distinct layers based on the density, with heavier materials sinking toward the center and lighter materials rising toward the surface. This is similar to what happened within the Earth, where the densest iron sank to form our planet's core, while lighter silicate rocks formed the mantle and crust. For differentiation to occur, a body must have been warm enough at some point in its history for its interior to become fluid, allowing gravity to sort the materials into layers. The fact that Ganymede is differentiated while Callisto, as we shall discuss shortly, appears to be largely undifferentiated, tells us that Ganymede experienced significantly more internal heating than its neighbor, despite their similar sizes and compositions. The interior structure of Ganymede, as scientists currently understand it, consists of several distinct layers. At the very center lies a core of iron or iron sulfide, which may be partially molten and responsible for generating the magnetic field. Surrounding this core is a mantle of silicate rock, similar in composition to the rocks that make up much of the Earth's interior. Above the rocky mantle lies a thick shell of ice, perhaps several hundred kilometers deep, and within this icy shell there may exist a layer of liquid water, a subsurface ocean trapped between layers of ice at different pressures. The outer surface of Ganymede is composed of water ice mixed with darker materials, and this surface displays a fascinating variety of terrains that record the Moon's geological history. The possibility of a subsurface ocean within Ganymede is particularly intriguing, because liquid water is considered one of the essential ingredients for life as we understand it. Evidence for this ocean comes from several sources, including observations of how Ganymede's magnetic field interacts with Jupiter's much larger magnetic field, and from theoretical models of how heat might be distributed within the Moon's interior. The ocean, if it exists, would be sandwiched between an outer layer of ice at the surface and deeper layers of ice at higher pressure, because water ice can exist in several different forms depending on the pressure it experiences, and at the pressures found deep within Ganymede, ice would take on denser crystalline structures that would sink below liquid water. This means the ocean would not be in direct contact with the rocky mantle below, which has implications for the chemistry of the water and for the potential for life, since interactions between water and rock are thought to be important for creating the chemical energy that life might use. The surface of Ganymede displays two main types of terrain that tell us about the Moon's past. About 1/3 of the surface consists of dark, heavily cratered regions that are quite ancient, perhaps 3 to 4 billion years old, representing the original surface of the Moon that has been bombarded by impacts over immense stretches of time. The remaining 2/3 of the surface consists of lighter, grooved terrain that is somewhat younger, perhaps 2 to 3 billion years old, and this terrain is particularly interesting because it shows evidence of geological activity in Ganymede's past. The grooves are long, parallel ridges and troughs that stretch across the lighter regions, sometimes for hundreds of kilometers, and they appear to have formed through a process of tectonic extension, where the icy crust was stretched and pulled apart, creating these distinctive linear features. The presence of this groove terrain tells us that Ganymede was once geologically active, that forces within the Moon were strong enough to crack and reshape its surface, creating new terrain that partially erased the ancient cratered landscape. This activity required heat, and the question of where this heat came from leads us to one of the key differences between Ganymede and its neighboring moon Callisto. Callisto orbits Jupiter at a greater distance than Ganymede, taking about 17 Earth days to complete one orbit compared to Ganymede's 7 days. And this difference in orbital position has had profound consequences for how the two moons evolved. Callisto is nearly as large as Ganymede, with a diameter of approximately 4,821 kilometers, making it the third largest moon in the solar system after Ganymede and Saturn's moon Titan. Like Ganymede, Callisto is composed of roughly equal parts rock and ice, and yet the two moons could hardly be more different in their current states. The surface of Callisto is ancient and heavily cratered, bearing the scars of countless impacts accumulated over billions of years. Unlike Ganymede, there are no groove terrains, no evidence of past tectonic activity, no signs that the surface was ever renewed by geological processes. Callisto's surface is essentially a record of bombardment stretching back to the earliest days of the solar system, making it one of the most ancient surfaces we can study anywhere. The most prominent feature on Callisto is the Valhalla Impact Basin, a truly enormous structure that stretches approximately 3,800 kilometers across, consisting of a bright central region surrounded by concentric rings that ripple outward like the frozen echoes of the ancient impact that created them. Valhalla is one of the largest impact structures in the solar system, and its preservation on Callisto's surface tells us that no geological processes have acted to erase it over the billions of years since it formed. Studies of Callisto's interior suggest that it is not fully differentiated like Ganymede, meaning that the rock and ice within the moon have not completely separated into distinct layers. Instead, Callisto appears to have a more mixed interior, though there is evidence suggesting it may have a small rocky core and possibly even a thin layer of liquid water deep beneath its surface. The degree of differentiation is significantly less than at Ganymede, and this tells us that Callisto never experienced the same level of internal heating that allowed Ganymede to fully separate into layers. Callisto appears to be a relatively primitive body, one that has changed little since it formed, offering us a window into the conditions of the early solar system. The question of why Ganymede became a differentiated, geologically active world while Callisto remained ancient and relatively unchanged is answered by considering their positions within Jupiter's system of moons. Ganymede exists in a special relationship with two of Jupiter's other large moons, Io and Europa, called an orbital resonance. For every one orbit that Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This is described as a 1:2:4 resonance, and it is maintained over billions of years by the gravitational interactions between these 3 moons. The significance of this orbital resonance is that it keeps the orbits of these moons slightly elliptical rather than perfectly circular, and an elliptical orbit means that the distance between the Moon and Jupiter changes throughout each orbit. As the Moon moves closer to and farther from Jupiter, the enormous gravitational pull of the giant planet flexes the Moon's interior, squeezing and stretching it slightly with each orbit. This repeated flexing generates heat through friction within the Moon, in much the same way that repeatedly bending a piece of metal causes it to become warm. This process is called tidal heating, and it is responsible for the intense volcanic activity on Io and the maintenance of Europa's subsurface ocean. Ganymede, being part of this resonance, experiences tidal heating as well, though to a lesser degree than Io or Europa because it is farther from Jupiter and the tidal forces are weaker. Nevertheless, over billions of years, this additional source of heat was enough to warm Ganymede's interior sufficiently for differentiation to occur, for the rocky material to sink and form a core, for the metallic core to remain warm enough to sustain a magnetic dynamo, and for the surface to be reshaped by tectonic activity. Callisto, orbiting beyond this resonance, does not experience significant tidal heating, and without this additional energy source, it has remained cold and relatively unchanged, a time capsule from the formation of the solar system. The contrasting fates of Ganymede and Callisto illustrate a broader principle in planetary science, which is that the energy a body receives, from whatever source, profoundly shapes its evolution. Two worlds can begin with similar compositions and similar sizes, and yet end up in completely different states depending on whether they have access to ongoing sources of heat. In the case of the Jovian system, orbital position and resonance relationships determine which moons receive tidal heating and which do not, creating a diverse family of worlds around a single planet. Our understanding of both Ganymede and Callisto is set to improve significantly in the coming decade, because the European Space Agency launched a spacecraft called JUICE in April of 2023, which is an acronym for Jupiter Icy Moons Explorer. After a journey of approximately 8 years, JUICE is scheduled to arrive at Jupiter in 2031, where it will conduct detailed studies of Europa, Ganymede, and Callisto. The mission's primary focus is Ganymede, and JUICE will eventually enter orbit around this moon in 2034, becoming the first spacecraft ever to orbit a moon other than our own. From this orbit, JUICE will study Ganymede's magnetic field, probe its interior structure, search for evidence of the subsurface ocean, and map its surface in unprecedented detail. As we consider the future of human exploration beyond Earth, Callisto has sometimes been mentioned as a potential site for a human outpost, and there is a particular reason for this that relates to Jupiter's intense radiation environment. Jupiter possesses an extraordinarily powerful magnetic field that traps charged particles from the solar wind and from volcanic material ejected by Io, creating radiation belts far more intense than those around Earth. The inner moons of Jupiter, including Io, Europa, and to some extent Ganymede, are bathed in this radiation, which would be hazardous to human explorers and damaging to electronic equipment. Callisto, however, orbits outside the most intense regions of Jupiter's radiation belts, in a relatively benign environment by Jovian standards. This makes Callisto potentially more hospitable for human presence than the inner moons, despite its ancient and battered surface, because the radiation levels there would be far more manageable. And so Ganymede and Callisto continue their patient orbits around Jupiter, two worlds born together from the same primordial cloud, yet shaped by very different histories. One became a dynamic world with a differentiated interior, a magnetic field, and a surface that records past geological activity, while the other remained a witness to the ancient past, its surface a cratered chronicle of the solar system's violent youth. The difference between them is a story of heat and energy, of orbital mechanics and resonance, of how the subtle interplay of gravitational forces can determine whether a world becomes geologically alive or remains frozen in time. And now we come to the smaller companions, the ones whose names are less familiar, whose forms are sometimes barely more than tumbling rocks, and yet whose presence in their planetary systems tells us something quietly profound about the way orbits settle, about the way gravity sculpts, and about the long, patient processes by which debris becomes moon and wanderer becomes captured companion. These are the shepherd moons, the Trojans, and the irregular satellites, and they deserve our attention not for their grandeur but for the gentle, ongoing work they perform in the darkness, circling their planets in paths that have been refined over billions of years into something approaching, in their own modest way, perfection. Let us begin at Saturn, where the ring system that so captivates the eye is not merely a passive structure of ice and dust, but rather a dynamic environment shaped in part by small moons that we call shepherds. The term is apt, for just as a shepherd guides a flock, preventing the animals from straying too far in any direction, these moons guide the particles of the rings, their gravity nudging material back into place, maintaining the sharp boundaries and narrow structures that would otherwise blur and spread. And among the most studied of these shepherd moons are Prometheus and Pandora, two small and irregularly shaped bodies that bracket Saturn's F ring, the thin and braided ring that lies just beyond the main ring system, and whose delicate structure would be impossible without their gravitational influence. Prometheus was discovered in 1980 by the Voyager 1 spacecraft as it flew past Saturn, and Pandora was confirmed shortly thereafter, and together they revealed to us a mechanism that had been theorized but never before observed so clearly. Prometheus orbits just inside the F ring, while Pandora orbits just outside, and between them they constrain the ring particles to a narrow band. As Prometheus passes along its inner orbit, it moves slightly faster than the ring particles, and its gravity tugs on the nearby material, drawing some particles outward and pushing others into slightly different paths. Pandora, moving more slowly on its outer orbit, provides a complementary influence, and the result is that the F ring remains narrow, only a few hundred kilometers wide, despite the tendency of ring material to spread out over time due to collisions and gravitational perturbations. The shapes of these moons are themselves worth contemplating as you settle deeper into rest. Neither Prometheus nor Pandora is spherical, for they are not massive enough for their own gravity to have pulled them into round forms. Instead, they are elongated and irregular, with ridges and grooves that speak to a history of gentle collisions and surface processes we do not yet fully understand. Prometheus is roughly 136 kilometers along its longest axis, while Pandora is somewhat smaller, and both are composed largely of water ice, as are most of Saturn's smaller moons. They are pale and cold, reflecting sunlight with the soft brightness of fresh snow, and they continue their shepherding work without variation, orbit after orbit, as they have for longer than there have been eyes anywhere in the universe to watch them. Within the rings themselves, embedded in the gaps and divisions that punctuate the bright bands of ice, there are moons smaller still. Pan, discovered in 1990 through careful examination of Voyager 2 images taken a decade earlier, orbits within the Encke Gap, a 325-kilometer-wide division in Saturn's A ring. Pan is only about 28 kilometers across at its widest, and yet its presence is essential for maintaining the gap's sharp edges. Without Pan, the gap would fill in over time as ring particles drifted inward and outward, but Pan's gravity clears the region, sweeping up stray material and keeping the gap well defined. What makes Pan particularly interesting, and what we can picture as we breathe slowly and let the day's concerns drift away, is its shape. When the Cassini spacecraft returned close-up images of Pan in 2017, scientists and the public alike noticed that the moon resembles nothing so much as a piece of ravioli, that stuffed pasta with its rounded center and flattened rim. This distinctive form is the result of accretion, the process by which Pan has been collecting ring material along its equator over immense spans of time. As the moon orbits within the Encke Gap, fine particles from the surrounding ring settle onto its surface, but because Pan rotates and because the geometry of its orbit places the equatorial region in contact with the most material, the accumulated debris has built up into a pronounced ridge that encircles the moon's middle. The central body of Pan may be older and more consolidated, while the equatorial ridge is younger, fluffier, and still slowly growing, particle by particle, as the moon continues its endless circuit through the gap. There are other tiny moonlets embedded within Saturn's rings, objects so small that they were not discovered until the Cassini mission began its detailed survey of the ring system in the mid-2000s. One such object is designated S2004S6, a provisional name indicating that it was the sixth satellite candidate identified in 2004. This moonlet, if it can even be called that, may be only a few hundred meters across, barely distinguishable from the larger ring particles that surround it except by the subtle gravitational effects it produces and the faint propeller-shaped disturbances it creates in the nearby ring material. These propeller moonlets, as they are sometimes called, represent a transitional category between ring particle and true moon, and they remind us that the boundaries we draw in our classifications are often blurrier than we might prefer, that nature does not always sort itself into neat categories for our convenience. Let us now turn our attention to Mars, whose two moons, Phobos and Deimos, present a rather different story of origin. These are small bodies, Phobos measuring roughly 22 kilometers across and Deimos only about 12, and both are irregularly shaped, dark, and heavily cratered. For many years, scientists debated whether Phobos and Deimos formed alongside Mars from the same primordial material, or whether they are captured asteroids, objects that wandered too close to Mars and were snared by its gravity. The capture hypothesis has long been appealing because the spectral properties of these moons, the way they reflect light at different wavelengths, resemble those of carbonaceous asteroids found in the outer asteroid belt. However, capture is not a simple process. For an object approaching a planet on a hyperbolic trajectory, that is, a path that would carry it past the planet and back out into space, must somehow lose energy in order to become bound in orbit. This energy loss could occur through atmospheric drag, if the object passed through a thicker ancient atmosphere, or through tidal interactions, or through a three-body encounter involving another object. Recent research has complicated the picture further, with some models suggesting that farbars and DMOs might have formed from debris blasted off Mars by a giant impact, similar in concept to the formation of Earth's moon but on a much smaller scale. The question remains open, a gentle mystery that continues to occupy planetary scientists, and we need not resolve it tonight in order to appreciate these two small moons as they circle the red planet, farbars drawing ever closer to Mars and destined, in perhaps 50 million years, to either crash into the surface or break apart into a ring, while DMO slowly spirals outward and may one day escape entirely. At Jupiter, the story of the smaller moons is one of remarkable abundance and diversity. As of 2023, Jupiter is known to have 95 moons, a number that has grown substantially over the past 2 decades as increasingly sensitive surveys have detected ever smaller objects in orbit around the giant planet. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, account for the vast majority of the satellite mass in the Jovian system, but the remaining moons, small and irregular and scattered across distant orbits, tell a different tale altogether. The irregular moons of Jupiter are thought to be captured objects, asteroids, or perhaps comets that approached Jupiter and, through various mechanisms of energy dissipation, became trapped in orbit. Many of these moons travel in retrograde orbits, meaning they circle Jupiter in the opposite direction from the planet's rotation and from the orbits of the Galilean moons. This retrograde motion is itself a signature of capture, for objects that form in place from a circumplanetary disk tend to orbit in the prograde direction, following the rotation of the central body, while captured objects can arrive from any direction and end up in orbits that reflect their original trajectories. The retrograde irregular moons of Jupiter are grouped into several families, clusters of moons with similar orbital characteristics that may have originated from the breakup of a single larger captured body. Among these distant retrograde moons, there is one that moves in the prograde direction against the general traffic of its neighborhood, and this is Valetudo, discovered in 2018 and given a name from Roman mythology, the goddess of health and hygiene. Valetudo is tiny, perhaps less than a kilometer across, and it orbits Jupiter at a great distance, taking roughly 530 Earth days to complete one circuit. What makes Valetudo remarkable, and what earned it the informal designation of an oddball moon, is that its prograde orbit carries it through the region populated by retrograde moons traveling in the opposite direction. The geometry of this arrangement means that collisions are not merely possible but, over the long span of solar system history, probable. Valetudo and the retrograde moons it passes among are on crossing orbits, and while the vastness of space means that any given close approach is unlikely to result in impact, over millions or billions of years, an eventual collision becomes increasingly likely. When such a collision occurs, it will not be a dramatic event visible from Earth, but rather a silent grinding in the darkness, producing fragments that will themselves become new moonlets, continuing the cycle of destruction and creation that has shaped the irregular satellite populations of all the giant planets. We may now travel outward to Neptune, where the small inner moons perform their own quiet orbital choreography. Among these are Naiad and Thalassa, 2 moons discovered by Voyager 2 during its 1989 flyby, each only a few tens of kilometers across. What makes their orbits noteworthy is the relationship between them, a pattern that scientists have described as a dance of avoidance. Naiad and Thalassa orbit Neptune at similar distances, with Naiad slightly closer to the planet and therefore moving slightly faster. Under ordinary circumstances, the faster inner moon would periodically catch up to and pass the slower outer moon, and if their orbits were in the same plane, close approaches would be frequent and gravitational interactions might eventually destabilize the system. But Naiad's orbit is tilted, inclined relative to Thalassa's orbital plane, and the 2 moons are locked in an orbital resonance that ensures they never come too close to one another. For every 73 orbits that Naiad completes, Thalassa completes 69, and this ratio means that whenever the 2 moons might otherwise approach each other closely, Naiad's tilted orbit carries it above or below Thalassa, avoiding a close encounter. This resonance is self-maintaining, a stable configuration that the moons will occupy indefinitely, weaving past each other in a pattern that is mathematically elegant and gravitationally harmonious. It is the sort of arrangement that invites metaphors of dancing partners, though of course the moons know nothing of dance, and their avoidance is simply the outcome of physics playing out over billions of years until a stable solution was found. Also at Neptune, there is Hippocamp, a tiny moon discovered in 2013 through analysis of Hubble Space Telescope images. Hippocamp is only about 34 kilometers across, making it one of the smallest moons in the Neptunian system, and it orbits close to Proteus, the largest of Neptune's inner moons. The proximity of Hippocamp to Proteus, and the examination of Proteus itself, led researchers to propose that Hippocamp may have been born from debris blasted off Proteus by a cometary impact. Proteus bears a large crater called Pharos, and the material excavated from this crater may have been sufficient to coalesce into a small new moon. If this hypothesis is correct, then Hippocamp is a second-generation moon, a child of Proteus in a sense, and its existence speaks to the ongoing processes of creation that continue even now in the outer solar system, where impacts still occur, debris still spreads, and gravity still gathers. These small moons, the shepherds, and the captured wanderers and the resonant dancers, are easy to overlook when the great moons of the solar system command so much attention. But they are everywhere, circling the planets in their thousands if we count the smallest ring particles that blur into moonlet status, and they remind us that the solar system is not a static arrangement but a living, evolving structure, still settling, still adjusting, still finding new equilibria. The shepherd moons will continue to guide their ring particles, the irregular moons will continue to trace their tilted and eccentric paths, and somewhere out there, Valetudo will continue its prograde journey through a retrograde neighborhood, patient and unaware of the collision that may await it. And so we can rest now, knowing that these small moons keep their vigils, that the rings they shepherd gleam in the distant sunlight, that the orbital resonances they maintain will hold through the night and through many nights to come. The solar system hums with these quiet motions, these gravitational arrangements, these ancient captured wanderers still circling the planets that caught them, and there is nothing we need to do but breathe slowly and let these thoughts settle like fine particles drifting onto the equator of a small ravioli-shaped moon, building up layer by layer, unhurried and patient as the turning of the worlds.